President of the Academy of Sciences of Bologna. And it is my pleasure to welcome you, all of you, in this building, which is the building where the Academy is hosted since many centuries. The Academy was founded at the end of the 17th century, and its activity is always in this place, in this building, in this old building, with these magnificent frescoes of Pellegrino Tibaldi at the end of the 16th century. So I am not an economist, I am a medical doctor, so I just want to welcome all of you here, and it's my pleasure to open this international workshop, Complexity in Socio-Economical Systems, the Connectivity Approach, which is organized by our friends and members of this academy, Professor Roberto Scazzieri, Professor Aura Reggiani, and also by Professor Ivano Cardinale. So now I give the microphone and the direction of the meeting to Professor Scazzieri, I think, or to Professor Mirko degli Esposti, please.
Thank you very much. Let's start. Let me thank again the President of the Academy for the introduction. And before we start, let me give a personal thanks to the organizer. I want to thank Ivano Cardinale and Professor Roberto Scazzieri, but a particular mention I'd like to give to Professor Aura Reggiani, which, if you, Professor Scazzieri, agree with me, the main engine of this very nice initiative. I'm also not an economist, but that's good, because we are talking about a very multidisciplinary problem. And I would like, first of all, to start with the presentation of a special issue, which is at the center of the workshop. And I don't want to waste time. We try to stay in line. So I really would like to give the stage to Professoressa Aura Reggiani and Dr. Ivano Cardinale and Professor Roberto Scazzieri for the presentation of a special issue. Thank you, Aura, again for your effort, organization, and the talk you're going to give now.
Thank you, Mirko. And first of all, I would like to thank Professor Bolondi and Professor Monari, who supported us for this initiative. So I'm very happy about it. And I would like to thank all the colleagues and friends that are, thank you, Mirko, that are with us. And also particularly Professor Fritz that came from the United States for this event. And my slides will be just a short introduction, and then I will leave the floor to Professor Scazzieri, Professor Cardinale. And just would like to say a few words why this conference and this workshop, and why so. So the idea is emerging from a special issue that we published in the journal Networks, Spatial Economics, and Professor Fries is the editor-in-chief since 2001. And also this idea emerged from the ALMA idea project on interconnectivity and resilience that was directed by Professor Campaner. And from that ideas, so several follow-up ideas research emerge. One of these is the relevance of connectivity architecture. And my presentation today, my short presentation, will be about the role of connectivity architecture in complex networks. So this was the starting point, so the paper that has been published in Network Spatial Economics. And then in this, my idea was the following. So I just realized that in 1962, Herbert Simon wrote a paper, The Architecture of Complexity, by focusing on hierarchical levels of a network. And 45 years later, Barabasi wrote an article with the same title, The Architecture of Complexity, in which he emphasized more the role of network dynamics. And then I started to think about the role of the architecture of connectivity. And mostly, can the network architecture of connectivity be considered the usual framework also for resilience and vulnerability issues that were the core, in a way, of our ALMA idea project, and possibly also to be discussed, the related limit to growth. I will not enter into detail now with the several definitions of vulnerability, resilience, because of course there is a lot to say. But concerning connectivity architecture, I will just say that there are two forms in a way: an explicit connectivity when there is vulnerability, shock propagation, and we can also mention the work by the Nobel Prize Ragnar Frisch in this respect, and hidden connectivity when we model theoretically, and then the hidden connectivity is in the coefficient. But what is also complexity? There are several definitions, and I like the first one of Simon again. So interaction in a simple way. And then, as I said, these interaction parameters play a role because they, in a way, connectivity is hidden in the interaction parameters in a dynamic model, and we can have also unstable behavior. But what about in network analysis? And here, connectivity is very explicit because it's found on topological form. So we can have the two extremes, the random form and the hub and spoke. And here is the role, in a way, of architecture connectivity, because the hubs can play a fundamental role. So my question is, are the more connected nodes from the topological viewpoint, like Barabasi, also the most important from the economic viewpoint in terms of innovation, growth, mobility? And we can observe a current increase of hub networks or network hubs. And is this an instrument for decoding complexity? And are network hubs, thank you. Are the network hubs able to capture the complex dynamics of the whole system, also in terms of vulnerability? So in the past, we are looking at the city network of 17 cities in Germany crossed by high-speed train, and we found that they were covering 60% at least of employment. So also, if you look at the capital regions in the European Union, we can see that the capital region had a high increase of GDP, also in the eastern country, and while the peripheral city were, of course, decreasing. So my final consideration are, so connectivity as a fundamental role for creating various network architecture, and mostly the hierarchy of hubs. And thanks to the network connectivity architecture, we can have new equilibria. That means that we can have vulnerability, but also thanks to connectivity, we can have also resilience. And with new equilibria, we can have also new opportunity. So we can consider a sort of Kuznets N-shaped curve where the connectivity indicators are able to create hubs, but then we can have maybe fragility or vulnerability, but then thanks again to this connectivity, we return to resilience. So there are different shape, dynamic shape of these phases. So my final then conclusion is the following. Are we going from the concept of network vulnerability resilience to network hubs? And mostly the research question that might be the follow-up of this workshop or this paper, how can we map out the dynamics of various types of hubs? We have seen that some hubs decline, some emerge, and so on, and so different typologies of hubs. So what is the role of network hubs, not only of connectivity? And then theory, measurement, policy, and I think that we need a multidisciplinary perspective. And for that, I would like to leave the floor to my colleague, Professor Scazzieri and Professor Cardinale, who can also more or less show us the beautiful road towards a new idea in this respect, the architecture of connectivity and also relative invariance and decomposability, so the structural approach to network complexity and resilience. So thank you. Roberto, if you can start.
Thank you. If you agree, I think we will do the three talk and then together, and then eventually we collect questions or comment at the end. So I really would like to ask Professor Roberto Scazzieri. Yes. And then, thank you.
Thank you. Okay. Well, thank you. And just just a few words of introduction, which I think relate to what Aura has been saying and to what also Ivano is going to say. Well, essentially, this set of introductions basically extracts certain questions, certain issues from what was discussed in the special issue, which gave the origin to this workshop. Hopefully, with the view of also introducing in a general way the three keynote speakers of this afternoon, and in terms of the following discussion, which hopefully will take place. Now, as Aura said, at the core of this special issue and at the core of the kind of discussion that we would like to encourage today is the role of connectivity and of its architecture. The notion of architecture, no, I'm just trying to use this. Which button should I? Oh, this one. Okay. The role of architecture is a central one, and I would like to emphasize that architectures are essentially a structural issue. Namely, I would like to call everybody's attention to the fact that when we are dealing with architecture, we are explicitly or implicitly referring to some degree of structural permanence. But in order to understand what we fully mean by structural permanence, I think we should go back to what Herbert Simon said in the well-known paper that Aura also referred to. Simon addressed our attention to the fact that when dealing with a complex system, one should unavoidably, from the cognitive point of view, emphasize and have recourse to some means of reducing its complexity. But what is a reduction of complexity in the case of a complex system based on interdependence between components? Here, Simon, again, argues that what is central is the kind of specification or visualization of interdependence. And he calls attention to the fact that very often, or almost unavoidably, this specification of interdependence is problem-driven. Well, but taking our starting point from this idea that problem-driven specification of interdependence, which is so central when addressing the issue of which architecture of connectivity are we dealing with, we unavoidably are facing the issue which was already suggested by Aura, namely this structure of interdependence may be hidden or visible, depending on which reduction of complexity we decide to follow. This is very much a logical implication of what Herbert Simon was arguing. Now, when dealing with identification of a specific structure of interdependence, if you want, with identification of a specific architecture of connectivity, we are dealing with the idea that we focus on certain relations, perhaps leaving other relations, other forms of connections aside. Here, there is an issue which I think comes up when dealing with the link primarily between which architecture of interdependence, which architecture of connectivity, and which dynamic path may follow out of that. And the issue of which dynamic path may follow from a certain specification of interdependence, from a certain architecture of connectivity, we are again dealing with the idea, which I may again refer to Herbert Simon, involves what Simon said about property of near decomposable systems. Simon was saying, and basically said that from the analytical point of view, but he was basically formalizing inadvertently, I would say, some ideas that was already well known in economics since the 1930s. I have in mind a well-known book work by Gunnar Myrdal, when he said that in a dynamic system, when the dynamic system is visualized as a system of components related to one another in terms of a certain pattern of connectivity, there is unavoidable what he called a certain order of motion between the different subunits subunits of a given network, because there are certain subunits which may react slowly, other subunits which may react to certain external impulses more quickly, and so on and so forth. Basically, this emphasis on structural interdependence, which is the kind of elements that I think I'm trying to visualize now, starting from what Aura was saying, is that if we take a certain problem-driven specification of interdependence, following Simon's suggestion, then we call our attention to a certain pattern of connectivity, leaving other patterns of connectivity aside. And basically, for what is the pattern of connectivity that we have decided to focus on, there is explicitly or implicitly the idea that this pattern of connectivity is something which we can take as given. So there is a principle of relative structural invariance at play here. But the point is that since, again, following Simon, specification of connectivity, a certain specification or visualization of the architecture of connectivity is essentially problem-driven. It depends on our point of view in terms of solving certain problems. Then what comes up and what logically derives from this line of argument is that we can actually, depending on which architecture of connectivity we decide to focus on, that we basically single out certain patterns of invariance relatively to others. So we visualize certain orders of motion instead of others. Eventually, we visualize certain, or the possibility of certain dynamic paths instead of other dynamic paths. So this plurality of dynamic paths was at the core of the spatial issue that we edited. And I just finishing, I'd like to read with you a sentence from our introduction, jointly written by Ivano, Aura, and myself. We said the propagation of disruptions takes place through channels provided by explicit or hidden connectivity between various units, such as countries, regions, productive sectors, and socio-economic groups. So essentially, what comes up from what I said in the previous slides, this idea of problem-driven specification of connectivity, or problem-driven visualization of architecture, involves an attention for plural specifications of interdependence, which eventually entails, for what we've just seen, the possibility of plural dynamic paths. Now, basically, well, these are issues that I think I'll have an opportunity to go back again while giving a short introduction to the session I'm supposed to co-chair. And I would like to finish my short introduction calling attention to certain research questions that I think stem from from this special issue, and which would be very nice if this workshop would be helpful in calling some attention to. Namely, in which way, this looks a very general question, but it's implicit in what I've just said. In which ways can theory inspire empirical work? Because theory has to do with the specification of connectivity, with the architecture of interdependence we decide to adopt as our starting point. Second research question, more specific research question, I would say connected with what Terry Frisch is going to argue in his presentation. How can network design, which is at the core of his paper, how can network design influence the dynamic trajectory of a complex network, the dynamic path that a network might follow? Third question, how can structural specification influence the path which may be followed by a circular economy, which would be the core of the second keynote speakers? And last but not least, in which ways can structural specification, the kind of structural specification, the kind of specification of interdependence we adopt influence identification and implementation of policy objectives. So this is actually what I wanted to say now. Thanks.
Thank you, Roberto. I think we'll wait before thanking all of them. We give a word to Ivano Cardinale. Thank you for your questions. While Ivano is preparing, I can say that they are very interesting research questions. In fact, I personally don't have an answer to any one of them. Only probably the second one we have partial answer, but then I will leave the expert to say more. And now we finish with the presentation of a special issue with a small, short talk or contribution by Dr. Ivano Cardinale from the University of London. Thank you very much, Ivano.
Thank you. Thanks for the introduction. So I will be briefly speaking about what can be seen as the third main theme of our special issue and of our workshop today, which is within these spaces, these systems of connectivity that Aura and Roberto so nicely presented, how do we pursue collective objectives? So is the realm of policy, if we want, or also the realm of politics in some ways within these systems. And so one focus in the special issue and in the work of some of us is on the production system and on the connectivity of this kind of system, so production systems. Now, there is, of course, a very important tradition in economic thinking that starts from physiocracy through the classics and the 20th century reprise of that understanding of the economy, very much based on connectivity, for example, in terms of input-output, you can think it, so of connections in terms of material flows or also in terms of expenditure and so on. So this tradition can be seen as studying system-level dynamics of production and distribution, meaning not the production and decisions at the micro level, but how the system as a whole produces and distributes the value of what is produced. Now, I would argue, and has been argued indeed, that there are two ways to understand these system-level dynamics. One is as dynamic laws or dynamic tendencies of industrial economies. So the idea is we try, for example, to replicate some stylized fact or through a model to get a sense of what a dynamic trajectory might be given some premises. But there's also another one, which is to think of these dynamics as systemic requirements for pursuing collective objectives. What's the idea there? Is that since there is connectivity pattern to a given material system, think about industrial production, for example, there are some objectives that can be achieved and some that cannot in any given moment. And these models, these theories help us think about what needs to happen in order for these objectives to be achieved. For example, reproductions of means of production with a surplus, meaning the economy being able to stay stationary or even grow, has some requirements in terms of the proportions between different sectors because they have to produce the output for the other sectors. Otherwise, production cannot go on at the same level. Or maximum growth. Are there any limits, any bottlenecks on the maximum growth rate at which a given system can grow? Turns out there are. Or full employment, typical Keynesian approach, has been, for example, by Passinetti, generalized to a growing and multi-sectoral system where the conditions for that kind of system to achieve full employment can be specified and have been specified. So I think this is a dual way to think about these models as descriptions of dynamics or as conditions for pursuing objectives. I also want to add a specific kind of systemic requirement, which is on the transitional path. And I think a good example is the energy transition. So it's widely shared that we want an economic system and production system with lower emissions, but we cannot invent them from one day to the next, even if only because they are based on a material infrastructure, on factories, on ways of producing, on existing technology, existing machinery, that in order to be changed has to be produced in turn, and so has the machinery to produce that machinery. So if we think in terms of this interconnection, moving from one initial state highly carbon intensive to a net zero or low carbon intensive one is not just let's invest enough or let's decide to change it. We have to specify what the transition paths are. And this is a different order of requirement that we would do well, I think, as a society to keep in mind and where these models can help. Now, since we are talking about pursuing collective objectives, who is supposed to do that? So who are the relevant actors, meaning at the aggregate level, not individual actors, who are supposed to put the decisions in place that can make the objectives come to fruition? Well, as economists, but it's a more general advice, I think, we tend to assume that there will be what we could call a systemic actor, like a government or the famous policymaker who will do it. This here is the Leviathan from the first edition of Hobbes. So famous impersonation of the state was supposed to express, to decide for everyone to avoid anarchy. But the reality is that, first of all, sometimes there is no systemic actor. Think about the international system. There isn't one actor that has the mandate or the power to pursue collective objectives on behalf of everyone. And we are seeing the consequences of that every day. But even where there is one, such as in national context, it's never absolute power. There are always social groups that have their own objectives, they have their own worldview, and making systemic collective objectives happen is about negotiation often. It's about making sure that sufficient political will can be mastered. What is interesting, and I think flows from what Taura and Roberto were saying, is that a given connectivity space, in the material sense, does not determine what the relevant aggregations are. So, for example, in the industrial economy of a given country, or even more the world, what will be the relevant social groups? Someone from a classical Marxian background will say classes, someone will say industries, someone will say something else. The truth is that they're all possible, but which ones will emerge in a given moment? Well, often in economic analysis, but also in other social sciences, we assume ex ante who the groups are. We say these are the classes or these are the groups. We know their payoffs. We know what they want. We know how they will interact. But in reality, that's not necessarily the case. We have to reconstruct those. And in order to understand that, we need to think about how the actors themselves see who they are. So is there, class consciousness of the all kind? Are there industries that stick together? Are there social groups defined in some other ways that try to influence policy decisions, and how? And so what emerges from this, if we want to do what we could call a political economy of connectivity, is that there are many potential actors, systemic, subsystemic. They face possibilities offered by the connectivity pattern, but also requirements if they want to pursue those patterns. And from that means that in reality, there is a variety of potential conflicts of interest in society, different policy spaces that depend on how different actors see the system, and different dynamic paths. So to conclude, just a couple of points. Rather than research questions, these are probably just questions that emerge from this kind of reasoning. So in a connectivity system, what are the policy spaces? Because we often tend to think in abstract terms. We want something to be achieved, but what does that connectivity space afford? So what are the affordances and the constraints? Affordances and constraints, first of all, for systemic objectives, for the collective objectives, but then we should ask ourselves what the relevant system is. Because, one, for example, can think within a country how distribution should happen, but without looking at the changes in production across the global economy that are happening, it might be idle to discuss what distribution in a given country should be like. It's embedded in a profound and unavoidable way within a broader system. So where to draw the boundary from an analytical point of view, and then from a political point of view, is not obvious. It's part of the analysis. And also for particular objectives. So if a social group wants to achieve a certain objectives, what can it do in that context? Through which political strategy? And finally, since we always hope as scholars, as analysts, to have an impact, is it possible that if we see the system differently, and Aura and Roberto have spoken about the fact that a given system could be represented in different ways, different reductions of complexity that are driven by different problems or different visualizations such as nodes or connection and so on, is it possible that by comparing different visualizations, we might see new possibilities or new constraints, or even new spaces for convergences between groups and interest that were not necessarily clear ex ante? Thank you.
Thank you. I think we can thank the speaker, and thank you again. If you can also leave the last questions or the slide, because we add more questions we don't have answers to the afternoon. I don't know if there are comments or questions about. I think I have one, but I will keep it for later. Yeah, and I suggest we move on. And I thank you again, all of you, for your contribution, and I will keep my comment and work and questions for after that. Now it's time to open it, the first section. Aura, please stay here, because let me say personally that as a researcher working on complex system, it is not only a pleasure, it's really an honor to have here Professor Thierry Fritz from the Pennsylvania State University. Let me say for the people who don't know, but a few of them, that Professor Fritz is from the Pennsylvania State University. I think is the first Inge Markov Professor of Industrial Engineering, and for me it's an honor because he gave fundamental contribution to various fields. Most of them are contained in the title of the speak today, which is Equilibrium, Network Design, Resilience, Connectivity, and Complexity. And while I ask you, Professor Fritz, to come to the stage, let me remember that he gave incredible contribution to the dynamic games and also application to logistic and transportation, optimization problem, network theory. So it's really a pleasure to have him here with us today, and I leave him the stage. And if you agree, I will let you know whether there are 5 minutes to the end or something like that, but please take your time, and thank you again for being here.
Okay. The word design was mentioned in the previous 20 minutes or so, and this is a perspective that I have on the design of infrastructure that takes the form of roadways and mechanisms to control traffic on roadways. I do not consider myself a traffic engineer. This is one level above where the engineering of the roadway actually happens. This is more strategic thinking than it is tactical. Okay. The next challenge is how to advance the slides. Here.
Also this.
Yeah, that's one.
Or
Okay.
probably
This one, no, this one.
You
Yeah,
can also,
that's
use,
one.
if you
Okay.
prefer, you can also, yeah,
Exactly.
but if you prefer, you can also use this one,
Okay.
as you wish, that one or that.
All right. My terminology may be slightly different than yours, so I'm going to review terminology quickly, not laboriously. Then I have certain topics that I'm going to discuss with you, different types of equilibria and optima, and then we'll talk about the price of anarchy and the braze of paradox, which are really the same problem articulated differently by professionals from different branches of knowledge. And then we'll talk about some statements of the equilibrium problems. And I have some thoughts about resilience and connectivity that are included. There we go. Two types of design. You may have heard these words before, especially if you're a game theorist. We have topological network design, which talks about changing the network, add a link, add a node, etc., or subtract from the network. Mechanism design, which is related to such topics as controlling traffic lights, if you were a traffic engineer, or setting congestion prices. They're a different beast, but they are related. Now, one of the first pieces of terminology in this talk to understand is what I mean by an atomic game. This is a confusing word, I think. It means that the game is so big, this competition that we call the game is so big that we don't really know how many players are involved. And we have to resort to some sort of fiction to classify them. And we claim that those in one particular class all make their decisions on the same thing, which is usually average disutility or average cost. And the identity of the individual agent is lost. So that's part of the story. It's not an approximation, it's part of the story. And a congestion game is going to be an atomic game that is describable as a Cournot-Nash game. It's non-cooperative. There's no collusion. Congestion games are about automobiles, but the phrase congestion game came to us from computer scientists. You can see the years here are sort of reversed. The first congestion games are dated in the 50s. Congestion games were studied in computer science in the 2000s. I like congestion games, so I've chosen it as a descriptor of the entire history of these things. And a Stackelberg game will be important to us. And then in my circle of colleagues, we use an acronym that really means the same thing, MPEC, Math Program with Equilibrium Constraints. And this terminology is abused routinely. If it's an optimal control problem or a variational calculus problem or some other type of problem, we still call it an MPEC. It's just part of the language. The Stackelberg leader has omnipotence. It can foresee what the other players are going to do, and those other players are Cournot-Nash players. And they are myopic. They only see what's in front of them at the current moment in time. Equilibrium network design is a Stackelberg game. Network design is normative. This frequently is confusing. It's about what should be what we want, but it's constrained by a positive model, a model of equilibrium. And that is something to keep in mind. Why study it? This is just my personal opinion. I don't think it's an important slide, but I'll be quick about it. The problem has important social impacts. There is something we call the price of anarchy. I'm going to talk to you about what it is. Turns out that if it's bounded, we don't have to worry about certain anomalies occurring. If it's unbounded, we've got a big problem. The Bayes paradox is the idea that we can add capacity locally and it will have a global degradation, or we can subtract traffic or congestion locally and it will have a global increase of congestion associated with it. It's not a paradox. It can be explained, and I'll do that. And we can introduce the topics that are of real interest to this body. They're not dissociated. Terminology. I don't know my audience, so I didn't know exactly what to write. I still don't. Maybe if you could remember a few letters. P for path, A for arc, F for the flow on an arc. Well, I should not say on an arc, F for flow, associated with some arcs. F with a subscript A is the flow on arc A. Similarly for H, it's about paths. P is an important set. It has a subscript, which is where you started, and another subscript, which is where you stop, where you headed. This will allow the models to be reduced to an extremely simple, elegant form that you may consider almost trivial. And I would be happy if they appear that way. D for delay. This is something engineers use. It means a disutility. If subscripted A, it's about an arc. Subscripted P, it's about a path. If it got a big M in front of it, it's the marginal value. All right? And I'll remind you of that, but that's all you need to know. Now, 1 and 2 are the meat of the problem that a lot of traffic engineers and economists and computer scientists have stressed and examined for part of their professional careers. It begins with a British traffic engineer who defined some concepts like this. And it's said that those influenced Martin Beckman, the famous spatial economist, to write down a mathematical programming formulation of this problem that I'm going to describe, which is user optimal. We don't have a cursor yet. I'm going to start with this definition here, even though the slide is written around systems optimal. So I'll be looking at number 2 when I start talking about it. If there's traffic that's non-zero, somebody actually journeyed on the path, it's because the delay or disutility is equal to a number that is the minimum value that's achievable in light of congestion. If the difference between the minimum value and the delay is considered, this surely has to be non-negative. It has to be positive. And those are the 2 observations that are needed. The only difference between this and systems optimal is that it's the marginal delay instead of the delay. And if you think about how in the theory of the firm, marginal products are all equal or marginal costs are all equal, you can see why number 1, which I didn't discuss, involving marginal costs, marginal disutilities rather, is a description of the minimum social cost that congestion could achieve. The classic function that traffic engineers in the static era of this problem, which is almost over. There's still people who actually pay their rent by dealing with this function and its implications, is a quadratic in flow F. It has some legitimate foundations, but it's not a strong foundation. It's been known as a weakness in this theory since inception. If we turn from a static world to a dynamic world, there was a recognition that that was necessary, and it was done in a very rigorous way. There's a wave equation for longitudinal waves in a channel. It's called by the 3 names of the mathematicians who researched it: Lighthill, Whittam, Richards, the LWR model. It's a system of partial differential equations with boundary conditions. It's got an unusual property. All of the classical solutions, that's all of the smooth solutions of it, are not physically real. So that there are discontinuities and shocks that are propagated in the channel. And that happens to be considered pretty close to the way traffic reacts. Have you ever been in a line of traffic and suddenly it slows down and nobody knows why? It's because it's a rarefaction wave where the traffic has propagated a disturbance ahead. It can be, of course, a jam, and the disturbance is propagated backwards. This system is no small thing to include among the constraints of your problem. But with some hard work, the system I described can be shown to have an operator. It's the solution of this system, and that this operator is continuous. We don't know anything really more than that. It's got to be dealt with numerically and can't be dealt with in any other satisfying way at this time. But the idea of a digital twin is very appealing. The idea that something would be running on the traffic network that would keep the solution of this sub-problem current and able to respond very quickly to what these delays are. I have not done that. No one has done that. But I would say that the theoretical foundation is there. Now, we come to the price of anarchy. Here's the language or a paraphrasing of the language in Roughgarden's dissertation. He says, well, if you can, at no particular cost to you, plug a new server into your local area network or your Ethernet, which means you're plugging it into the world's internet. How do you know that's a good thing? Maybe you're going to precipitate just a cascading failure. Why would you presume that's good? It's really hard to study on the internet. Why don't we abstract to a traffic network, a congestion network, and ask the same question? What is the most efficient solution for congestion? That's the so-called systems optimal solution, where you imagine a controller is saying, you go there, you wait a few minutes and then depart, so forth and so on. That forms the denominator. If you want to read that in symbolic terms, you can by referencing the list of symbols, but it's not important. That's the most efficient solution. Up top is the user equilibrium solution. And okay. And that ratio, if you think about it, has to be greater than or equal to 1. Nothing's great. Nothing can be more efficient than the numerator. So it's greater than or equal to 1. And Roughgarden's thesis was, if you can find a reasonable bound, you can forget about this problem. It's just a reasonable bound, and it's okay. He found a really nice bound for fixed demand, linear delay functions in a static realm. He found a general bound for the same setup, but the bound depends on some properties that are very hard to find. They exist, but it's very hard to acquire the numbers that correspond to these. So he has bullet 2 unnumbered, 3 unnumbered. And I'm not, and a lot of people aren't totally satisfied with this, but let's just say this is the static world, and it's pretty well under control. There is a bound on one special case of dynamic user equilibrium or dynamic congestion games by 2 mathematicians in Germany. It's not a general case. And for the general case, there's no bound on the price of anarchy. This suggests that we need to proceed with caution. And the Bayes paradox, I mentioned very rapidly in the opening remarks. Now I'll speak more slowly. It's the idea that I'll put it in the most general system terms, making a local improvement to a system could result in a global degradation or disimprovement. That's the paradox. So you add a link and congestion overall gets worse. Can that happen? There are numerous examples published, all right, for the static case. That paper I referenced is a secondary source. He worked on the results of another paper and presented in a highly readable form. I don't think this is necessary. When we go to the dynamic congestion game and we set aside the scribbling on the board, manipulating things, it takes this form. This is one of its forms, I should say. This is the delay on a path. This is a flow on a path. This is the solution. That is the equilibrium solution, has a little asterisk. And there's an asterisk missing here. If I had my iPad, I'd just mark it in there right now, but I can't. All right. This is called a variational inequality, and it's constrained by having these H's that do not have the asterisk be non-negative. That's the vector of all the path flows or departure rates. And that an appropriate sum over the all time from the start of your clock to the end of the clock, you could say this is the morning commute from 7 a.m. to 9:45, then a sum over all the paths integrated with respect to time is the demand. And there are some other ways to formulate it. Here is one of them. Now, I know I have some control theorists in the audience. This is a completely equivalent statement in the form of what's known as a two-point boundary value problem. And this, because the differential equation is expressed, is called a differential variational inequality. And the reason you notice the asterisk is here this time. This is important because although I'm not going to do it, it's pretty easy to apply the mathematics of optimal control theory to this problem. If you were trained in it, I could do a manipulation on number one that would set it up to be analyzed by the necessary conditions of optimal control. Now, I want you, those with the control background, to take a look at this. This is the state variable, and it only appears one place in the whole problem. It appears on the left-hand side of the differential equation. That means that this problem is going to have especially easy solutions. What it means is that the dynamic dual variables are going to turn out to be constant, and they're going to be equal to the minimum price of travel between the OD pair. And after a little training, you could get your class, your students, to do the calculation. It's not very hard. Now, what I didn't emphasize is that I parameterized this delay in terms of kappa here on purpose. This is the capital investment that's made in the network. And I'm going to write down a design problem next, and we will have completed all the really essential ingredients. The rest is much more informal. We represent this whole thing as the equilibrium flows are an operator in the capital investments in the roadway. What would that be? Expansion of the roadways. You could add lanes, and people often say, well, that can't be continuous. You can only add one lane. Oh, you can add different types of rules for the control of speed. Those are continuous. You can add ways of considering the capital as a continuum that I discussed during the question and answer period, I think, and you would be satisfied with the answers. So here is the object that I started with in mathematical forms now. It says, I'm going to minimize this capital outlay. It's delay times path flow, which is a total congestion in the network. It's parametric and capital. This is a budget constraint. It says this much capital costs G, and it has to be less than or equal to the budget. This is the equilibrium constraint. This is the fact that we're not going to destroy the road by shutting it down. Now, there can be some very interesting problems when you talk about disinvestment of infrastructure, but that's not in this model. This problem can be solved. It has with it the unfortunate aspect that we can't solve it for a known global optimum because it's non-convex. All network designs based on equilibrium have that property. Am I about done? Okay, I'll wrap up pretty quickly. We don't have time, but for maybe one of these or two of these here, I said, well, what's the relationship to resilience? Well, I could think that there's a time T1, if we were out of equilibrium, a time T1 when we wanted to be in equilibrium, F star. And I could divide this objective that's on the previous page so that there's a part related to the first step in time, T0 to T1, and then from T1 to TF. And look for congestion prices that would guide the users of the network to the appropriate routes to get back to equilibrium as quickly as possible. That's a resilience calculation that can be done today. All right. Connectedness. Here is an essay. I don't want to read it back to you. It says, maybe some people like the fact that some routes to work have points at which they can depart from their original planned route because they encounter some congestion. I don't know if you do that here in Bologna, but it happens all the time in major metropolitan areas in the States. And so some people may actually see when the number of such alternative routings that lie along your original route are considered that the physical delay is actually diminished by this psychological impression. That can be folded into the calculation with regard to the consideration of what does connectedness do to you. You can do a full option pricing analysis a la the financial literature, a real analysis, in other words, a real options analysis. And you can show that this kind of thing can also be done. And that would involve some uncertainty or stochasticity, if you're wondering about that. And I think we have to stop there. That's probably the end. I have plenty of time for questions, so. Yeah. Do we wait for questions or do them now?
Thank you. Thank you very much. I think we have a lot of time for discussion after this stimulating. Aura, you want to break the ice, please?
Yes. So I will be, first I would like to thank you for the illuminating presentation. And I would like just to ask a short question because I expected there are a lot of questions from the audience. And mine is maybe very simple. Since the conference, the workshop is on connectiveness and complexity. So I was wondering if I understood well your objective function in your optimal control is linear. And so I would like to ask you, what about to think about a disequilibrium in the path to equilibrium by considering a nonlinear function in your objective function and maybe also discrete time? So just to find some areas of disequilibrium. I saw that you wrote already a paper in 2004 with David on disequilibrium. So can you say something about disequilibrium also? Thank you.
Okay. The objective is nonlinear. Yeah. So there's no problem with that. The problem that does arise is that when the design problem is solved, you have a linear constraint representing the equilibrium. Remember, you have to constrain it by the behavior of the drivers. One easy way to think of that is just a fixed point problem. You know, F implicitly equals 0, and F depends on all the variables. Well, that as soon as you have an equality constraint that is nonlinear, and it would be, convexity is gone, all right, forever. And we have the problem of never knowing if we found the global solution. And you would most likely, if this was a really important problem, social problem, and this is an important caveat, that could be solved deliberately, meaning with enough time, then you would use some sort of search, you know, any of these computational intelligence schemes. If it has to be solved extremely rapidly, you could think in terms of things like digital twins, but you have non-uniqueness. You know, you're not going to know that you got a really good solution. So this, however, is not my personal human failing. This is the nature of such problems, but it's an important difficulty, real difficulty.
Thank you. Any other questions, comment? Please, Armando, can you come here? So, Armando? No, you have a microphone there.
I start from the last comment. So, for example, in practice, finally, we don't need the optimal solution. We need a good solution. So, in some sense, for example, starting from a practical problem like traffic in Bologna, we want to improve actual solution and to get a better solution. Well, we don't know if it's the optimal because I know that the space could be very complicated. So the question is to apply a control, in some sense, a control theory which look to improve a system. How much information we need? So if we start from a really practical problem, traffic in a road network, which information would you need to apply your approach in order to get an improvement of a state of traffic? And the second question is, when you talk about traffic, you cannot neglect the granular nature of traffic, which means fluctuations. And fluctuations for me is quite important to induce congested state, even if you are subcritical, for example, in some case. So how fluctuation enter in your approach?
On the first question, what I would need would be derivatives of my objective, which is some representation of welfare with respect to parameters that are in my control, like the K number, which could stand for capacity, signal control, speed limits, so forth and so on. And as you know, having that derivative, I could then adjust and see what the impacts would be. And I could do it in a formal way, but I could also do it in a somewhat ad hoc way and know certainly that I'm going to get a better answer. You know, I wouldn't accept an adjustment that produces less. It would have to increase. This is the theory in the digital twin, right? I mean, that's what they do. So I think that one's okay, as long as I can get at the derivative somehow. If I have some circumstance of non-differentiability, you know, I guess I'd approximate the derivative. Okay, you can approximate it, even if you can't collapse it in the limit to a real derivative. You could take a look at the change. There are generalizations of the derivative too. You know, so probably something can be done. I don't think I've read anything in the digital twin literature indicates anybody's thinking about non-differentiability, though, right now. So that would be an extension. Very interesting one. Second question, I want to be sure I understand it. You're talking about if there was and it's a question on my part now, if there was an event in the traffic stream. Yes, I believe it's possible, and this may strike you as questionable, but I believe it's possible to build a particle model. All right. The equations of motion are very simple. You know, you follow along your allowed path, you can't leave the roadway. If you want to get more sophisticated, you can say you can't touch another vehicle. I've done a lot of thinking about it. I think it can be formulated. The more constraints you add on the vehicle about what it can do in the stream, the more difficult it's going to be. But if you keep them not too complicated, I think a particle model can be developed, even for the whole network. I actually think so. I mean, dx dt equal velocity. Velocity could be a control. d2x dt squared, you could make acceleration a control. And as you know, traffic engineers since the 40s have measured acceleration noise. So you could even have a stochastic equation of motion with a very good foundation for saying that that's Brownian motion. And then you have availability of, I mean, I don't want to get too technical, but you could do mean field approximations and things like that that could be done to reduce this horribly high dimension problem to one where you could perhaps analyze it more quickly and so forth. I'm an optimist, okay, as you can tell. I think it would be a challenge. I think it would be exciting to do.
Thanks for your answer. Long life to optimism. Let me see if there is any other question, please.
I think that the key vector is a crucial vector, the vector to control the latencies of each arc. And besides the difficulties to apply these values to every arcs of the network, and this is obviously a practical difficulty. But my question is related to the dynamicity of the values of the entries of this vector, of this K vector, in consideration of the fact that the network is treated as dynamic. So the dynamicity of the network reflects the dynamicity of the key vector as well. So what do you think about this relationship between the dynamicity of the network and the dynamicity of the key vector?
Now, when you say key vector, do you mean the capital?
The capital investments to control each latency of
Right.
each link.
That's a very interesting question. Could you change the rate of investment or capital contribution over time? Yes, for certain regions, for certain types of investment. If you're talking about bridges, I mean, you're going to have a model with short time scale and long time scale. And that I haven't accounted for here. But it, you know, this is my optimism again. I think it could be done. There are systems of differential equations with differences or what do they call them? Lags or advances, shifts, time shifts. Those, when they're ordinary differential equations, are not more difficult or less difficult than any other ordinary differential equation. If the time shift is a constant, if it becomes dependent on the state variable, you're getting into a real mess. But I think it's again a very interesting problem and should be pursued. Maybe you guys should get together.
Thank you. Any other questions? Please.
Well, thank you very much, first of all, for an absolutely enlightening presentation. My question, well, I'm an economist. My question is on a slightly different issue. You said that your research program on network design has basically a normative foundation. You said that network design is normative, which of course means, as you suggested, that it has closely associated with our choice of objectives, of goals. Then you went on in your modeling, essentially calling attention on, if I understand you correctly, on actors' behavior and on different options that actors may decide to follow. For instance, you emphasize departure times and so on and so forth, and perhaps also how price dynamics, can actually change actors' behavior. My question is on a connected issue, because our ways and your ways of affecting actors' behavior seem to presuppose in any actual empirical case, the existence of a given structure of channels, so to speak, or structure of roads. So, I mean, is there any way, have you been thinking of any way by which network design, normative actor design, can also affect actors' behavior by adopting, by considering one configuration of channels of roads rather than another?
Right. I think I understand you. Almost every word I said here was about investment or investment variables that were continuous. And I think that's really one of your comments. And there's another whole side to network design, and that's where you consider discreteness. And I did not discuss that, where you add one feature at a time. You could add one path. You could add one arc. You could add one bridge. I mean, the problem, as you know, with that is integrality is what people call it, is non-convexity. And you're without then any great way of solving it. If you have just a limited number of variables that you want to see change from inactive to active in control theory or the calculus variations, you can do that using time. You could say, okay, the value of the variable is 0 or 1 or 0 and 5 or whatever. I'm going to just find when it changes. And time then is a continuum, it's a necessary condition. If I have necessary conditions, I always think I can find the answer. So I've never done what you're saying, but I think maybe for limited number of, A, B, or 0, 1 circumstances, that could be handled. If every driver, has to have 15 choices, I don't think you can do it.
Thanks.
Yeah.
Thank you. Thank you very much. Any other questions? Okay, so I go back to my duty, which is to keep the time, but let me thank again Professor Fritz for this nice introduction and for the answering to the questions. Before coffee break, I suggest we move to section 2, so we stay in time. I ask Professor Roberto Scazzieri to join me, and also Professor Luca Lambertini, which is also the director of our Climate Change Center at the University of Bologna. And I would like both of them, did you find the name? Good. Turn it on the other side. And I ask Roberto and Luca to help me to introduce us the next speaker, Professor Kiran Donaghi from the Cornell University Department of City and Regional Planning, which is connecting online and even virtually. I'm going to welcome here in Bologna, virtually.
Good morning. Good afternoon.
Good afternoon. Nice to see you. And I don't know, before we give you the word, if Roberto or Luca, Professor Lambertini, want to introduce him. Thank you very much, Luca, and thank you again. And thank you again, Kiran, to be here with us.
One question before we begin. Would it be possible for me to share my screen with you so that I can control the presentation?
Of course. You will be willing to share your slide with us on
Yes,
Teams.
absolutely.
Yeah.
All right. So welcome to the second session today. I'm Luca Lambertini. I belong to the Department of Economics of the University of Bologna, and I happen to chair the Interdepartmental Center on Climate Change of the University of Bologna. So I'm not exactly intervening as a pure economist, but I have hopefully a transdisciplinary task and accordingly a very horizontal view of these problems. And it is a great honor for me to welcome Professor Kiran Donaghi from Cornell University. And essentially the point is that we are looking at transdisciplinary analysis of problems involved in climate change, and this means a wide range of sub-problems interacting between themselves inside complex systems. And the presentation we are about to listen to is exactly in this vein, and this is testified by the career of our guest, which is featuring key contributions on climate change and environmental policy, the ethics of development, conflict resolutions, and international relations and international trade at the same time. So I'm very glad to have the possibility of listening to you, Kiran, and thank you very much for being with us today. The screen is yours. You should be able to share the screen with us. I think there is no problem with allowing you to do so. It should be ready, if I'm not mistaken. Yes. So please go ahead with your presentation.
Okay, we see it.
Yes.
I'm sorry, this is the wrong paper. I'm very sorry.
It's okay. It should be okay.
Yeah.
We see your slides.
Okay, let's still wanna. Here we go. Okay, good.
Okay.
Okay.
All right. Well, thank you very much for that kind of introduction. And I'm very pleased to be able to participate in this workshop, albeit on short notice. The material in this presentation is discussed in much greater detail in the paper of the same title that appeared in the journal Networks and Spatial Economics in 2022. Let me proceed here. So as my introducing partner said, this concerns circular economy, which has become a very topical issue at the moment. There's well over several thousand papers that have been published on the subject. And this concept is a characterization of how goods and services can be produced and consumed in an ecologically sound and environmentally sustainable manner that meets concerns of overuse of resources, waste management, and climate change, among other things, through the intentional interlinking of disparate economic activities. This idea has been adopted by a number of EU countries and by China as the basis of their approaches to economic development, and it has also been promoted by the World Economic Forum as a model for urban economic development in the 21st century. The notion of circular cumulative causation, through which certain effects are promoted and reinforced by positive feedbacks, is also not a new concept, and it played a prominent role in the development of economics of Thorsten Veblen and Gunnar Myrdal, and the growth theories of Nicholas Kaldor and Alan Thirlwall, but also in the new economic geography of Krugman and Baldwin, Martin, and Octaviano. However, little attention has been given to how our knowledge of circular cumulative causation, which is an emergent property of nonlinear dynamic complex systems, might be harnessed to bring about desirable systems properties, such as those of a circular market economy, and whether or not there might be gains from trade in resources and recycling technologies between countries with developed and developing economies. So the point of the research here presented is to extend a formal examination of how CCC might be used to manage the transition to a circular economy, which I presented earlier in the chapter in Auer's book on complexity theory, and to extend it to consider possible gains from trade. And this plays into the area of inquiry of Nancy Cartwright, a philosopher and economist who wrote a very influential book on hunting causes and then using them. So the plan of my talk is to review the concept of a circular economy as has been elaborated by the environmental resource economists Pierce and Turner, review the first circular model of economic growth developed by George, Lin, and Chen, quickly review the work that I've done based on an extension of George and all that includes several sources of endogenous circular cumulative causality, and then present a model of economic growth with trade in an environmentally polluting resource, other materials, and recycling technologies. I'll conclude by discussing next steps in a research agenda. I should say at this point that in the paper that's published in Networks and Spatial Economics, I do make connections to the architecture of complexity and the architecture of connectivity as developed by Roberto Scarziari and Aura Reggiani, but given the limitations of time here, I can't explore those dimensions of the subject. So if we think about the conventional model of an open-ended economy, we have resources being extracted, and some of those resources are used to produce capital goods. Capital goods and the resources are used to produce goods that are consumed and which lead to amenity value of some sort, and then are discarded in the form of waste. A more complete assessment of a circular economy, which is provided by Pierce and Turner, and this really comes out of the field of industrial ecology, although much of the work in circular economics is now residing in the neoclassical environmental economics field. But here we have a very detailed flow of materials which are guided by values. And so we start again from the extraction of resources. These could be exhaustible resources or renewable resources. And the key here in each case is not to harvest more than the yield. If they're exhaustible resources, you will eventually be running them down. But renewable resources, we can think about forestry products and fisheries, et cetera, can be overfished or overcut. But if they're managed properly, then we maintain the resource. And the resource is so extracted can be used again in production, and production leads to consumption, which leads to amenity value. This process leads to waste, and some of that waste could be recycled. Other of it could be assimilated, but if the waste exceeds the assimilative capacity of the economy, we run into problems with negative amenities. So this is a more complete and insightful characterization. I want to say at this point that the work that George and all have been doing and the work that I've been doing does not completely capture this characterization, but we're working on including more and more features. So in their 2015 paper, George, Lin, and Chen present a theoretical model of economic growth that incorporates the concept of circular economic activities. So this is a very abstract and simplified growth model, but it enables them to make a certain point. And we need to bear in mind that each model is a set of assumptions and logical implications that supports a thought experiment. And so this is their thought experiment. They considered a closed economy with zero population growth. A social planner is assumed to exist, and this planner maximizes a social welfare function equal to the discounted present value of a future utility stream, which depends on aggregate consumption and the stock of pollution. In this function, U of CP is the instantaneous utility function, and C and P denote consumption and pollution. Rho is the rate of time preference, and the utility function has standard properties, by which we mean that utility is increasing in consumption at a decreasing rate and is decreasing in pollution at an increasing rate. So output, Q, is produced by a concave production function, phi, using two factors of production, X, which represents a periodic rate of use of recycled resources, and Z, which is a periodic rate of use of an environmentally polluting resource. Now, a key equation in this model, which also poses problems later on, is that the stock of waste accumulates by residual according to a balance equation, which you see in the middle of the screen. And so we're subtracting from production goods that are consumed, periodic use of the polluting resource, and the activity of converting waste to something that's recyclable and usable. Recycling turns waste into a useful factor of production so that we can replace X with beta S. And upon substitution, the waste equation becomes the one you see at the bottom of the page. The level of pollution generated in this economy depends on the amount of polluting resource used, theta, recycling ratio, beta, and the self-renewal capability of the natural environment, delta. Now, given the laws of motion governing the accumulation of waste and pollution, the social planner chooses control variables for consumption and the use of the polluting material to maximize the social welfare function. And if we allow lambda and mu to denote the co-state variables for S and P, the evolution of the circular economy can be analyzed by setting up the appropriate Hamiltonian function for a constrained dynamic optimization problem, and then differentiating it to obtain first-order necessary conditions for an optimal solution. And these conditions are as follows. George and all manipulate these expressions to develop dynamic equations in the control variables depicting the growth rates of consumption and the use of polluting resource. From the equation characterizing optimal growth and consumption, which is a modified Keynes-Ramsey rule, we have the equation you see at the top there. Now note that since UCC, the second derivative of utility with respect to consumption, is negative, that coefficient in brackets will be positive. And the Keynes-Ramsey rule says that we modify our consumption according to whether or not the rate of interest exceeds the rate of time preference. So from this equation, one can see that the marginal product of the recyclable input, phi or phi sub x, affects this rate. the growth rate will decrease with a higher rate of time preference and increase with the recycling ratio. If the cost of using Z, the polluting input, increases, the social planner will substitute the recyclable input for the polluting input, and the optimal rate of economic growth will increase. According to this equation, consumption is increasing when phi sub x is larger than phi sub z, and when this is no longer the case, then the rate of change in consumption turns negative. Now, from the equation giving the optimal time path of the polluting resource usage, we can see that the rate of change in the quantity of the polluting resource employed depends on the proportionate rate of change in the shadow price of the resource and the usage of the recycled. George and al. Infer from this equation that the level of pollution increases as the economy grows. However, when the economy begins to slow down and consumption decreases, pollution continues to increase, implying that there is a departure from sustainability. Finally, they conclude that environmental quality cannot be maintained or improved via economic growth. This is a very dour conclusion to arrive at. They depict these relationships in the following figure. Okay, and we don't have much time to unpack this, so I'll move on. To introduce circular cumulative causality, back in 2021, I accounted for 3 potential sources of CCC, and these are increasing returns to scale in production, learning by doing in recycling, and increased efficiencies in the use of a polluting resource through human capital deepening. To allow numerical analysis, I adopted explicit specifications for the intertemporal utility function, in this case an isoelastic function, and the production function, which is an increasing returns to scale constant elasticity of substitution function. And I also included physical capital, human capital, labor, and other materials as productive factors. The optimization problem for the social planners is now to choose control variables C and Z, but also investments in physical and social capital to maximize the present value of welfare. The state equations of this extended model are now as follows. So we have the stock of waste equation of motion, which is augmented to include 2 kinds of investment. And the aggregate output equation now brings into play not only those new material inputs and factors that I noted above, but also a variable conversion ratio from waste into recyclable materials, which depends on the accumulated recycling that's going on in this case. Stock of pollution also includes a variable coefficient, which takes into account the amount of human capital deepening that's going on. And you will notice that there's a small kappa in the exponent for the bracketed expression in the CES function, and kappa allows for increasing returns to scale. And this is a function that was introduced by Henderson back in the 1970s. So the current value Hamiltonian for this problem can be written as you see here, which we now include the additional equations and the extended specification. The zero-order optimality conditions, the co-state equations, and the transversality conditions can be obtained in a manner similar to that presented for the model of George and al., but won't be presented and discussed here because of time constraints. But if you take a look at the 2022 paper, there are several appendices which lay out the derivation of all the appropriate expressions. To simulate the model, the optimality conditions, the co-state equations, and the transversality conditions were manipulated to obtain a mathematically equivalent set of conditions that are easier to solve numerically. The parameter values were chosen to conform to stylized facts as were the relative values of variables. And I employed information on solid waste generation per unit of GDP, pollution, and recycling from documents published by the state of Washington in the year 2014. So this keeps us tethered to reality. So what we see in the solution of this extended model is that the pollution stock dips below the waste stock, eventually as both stocks decline from recycling the waste. The economy grows, but the polluting resource is used less intensively. And here we see the human capital deepening as the solution of the model plays out. So this tends to counter the dour conclusion that was arrived at by George et al. Now, in a time when the use of polluting resources to produce and consume goods and services is intimately tied up with global supply chains, our analysis must extend beyond single economies. And in fact, George et al. Suggest as a next step, studying trade and resources and recycling technologies between countries with developing and developed economies. To study possible effects of trade and resources and technologies on the circularity of growth economies, when circular cumulative causation is present, we go on to consider a three-economy or three-country or three-region model in which there is a high-tech economy, economy A less well-developed economy that is resource abundant in the polluting resource, economy B, and a second less well-developed economy that is resource abundant in other materials that are used to produce gross output. As in the case of the previous two models, we assume that each of the three economies wishes to promote circularity and has a social planner whose optimization problem is to maximize the present value of a discounted stream of welfare, which is derived from consumption and pollution. We also assume that apart from the technologies determining the rates of recycling and pollution, preferences and production technologies, that is to say, the parameters of the utility and production functions, are the same for all three economies. Each of the social planners chooses trajectories of consumption and usage of the polluting resource and investments in physical capital. The percentage rate of change in the stock of human capital, HI bar, is now assumed to be set exogenously as a policy parameter in each economy to distinguish differences in social policy approaches. Now we're going to assume further that each economy can function in a state of autarky, that is to say, without engaging in trade. Each economy has a technology enabling it to recycle waste and sufficient supplies of the environmentally polluting resource and other materials to produce for its domestic needs. However, we shall now allow for the possibility of trade between the economies in the goods in which each economy enjoys a comparative advantage. We assume that the terms of trade are negotiated externally, but that the effects of trade will include a reduction in overall cost to countries A and C of the polluting resource Z, and a reduction in overall cost to countries A and B of other materials. And with trade in these goods will come an increase in pollution of the non-point source variety, which travel entails, or the shipment of resources. And the non-point source coefficients are denoted by phi OMI and phi ZI. In addition, economies B and C will gain the benefit of using economy A's recycling technology, for which they will incur a licensing fee R. But there is no increase in pollution associated with this technology transfer. It is reasonable to assume that economies will engage in trading if they can realize gains from trade in terms of greater welfare and less pollution, and otherwise not. So the state equations characterizing the behavior of each economy in a state of autarky are as follows. The stock of waste equation stays pretty much the same as it was. And once again, note that Q is aggregate output, not GDP, and the costs of investment and capital adjustment are assumed to be quadratic. Moreover, other materials are now included in the balance equation since they are potentially a traded commodity. And we have the stock of pollution pretty much as before, accumulated experience in recycling, physical capital investments, and we note that human capital investment is set by policy of the planner inside each of these economies. As in the case of the single economy model considered in the previous section, rates of growth in the use of labor and other materials in production are taken to be exogenously given. And the current value of Hamiltonian for the problem faced by the social planner in the absence of trade can be written as you see. The zero-order optimality conditions for the control variables, the co-state equations, and the transversality conditions can be obtained by appropriate differentiation of the Hamiltonian, but I'm not going to present them here because of time limitations. Now, to characterize trade between the economies, several modifications must be made to the state equations, determining rates of change in waste and pollution stocks and the zero-order optimality conditions for the polluting resource. And so the terms in red type here represent the trade that goes on over licensing fees imposed. And I guess there's nowhere else that needs to be said about that. Now, appropriate adjustments must also be made in the Hamiltonians for each of the three economies' social planners. So with this setup for the economies in autarky and the economies engaged in trade, we proceed to conduct two proof of concept simulation exercises. In the first, there is no trade, and each economy's social planner solves his or her dynamic optimization problem without the benefit of lower costs of resources or materials, or in the case of economies B and C, a more technically advanced recycling technology. In the second simulation, economies A and C import some of the environmentally polluting resource used in production, and thereby they lower the total cost of using resources. And economies A and B import some of the other material resources, also enjoying production cost savings. And economies B and C, which invest less than economy A in human capital formation, license the use of economy A's recycling technology. These are the parameter values that I've adopted, and they're also documented in the paper. And these are initial values of the variables and simulations scaled appropriately to enable a clean solution to be obtained. Each of the two simulations, the simultaneous solutions of the social planner's optimal control problems of the three economies, is conducted over 50 time periods. A ceiling on the use of the polluting resources imposed beyond the 40th time period to be the value of that time period to represent a target limit set by policy to reduce the use of the polluting resource, and investment in physical capital is bounded from below at 3%. They can't invest less than 3% in physical capital. So here we have a table of the solutions, and we can see that in each simulation, the presence of circular and cumulative causation helps the economies to increase circularity, which is to say that in each economy, pollution decreases monotonically after a certain point, even as growth continues. When trade in resources and recycling technology occurs, the pollution stocks of all three economies are substantially less than their waste stocks. The collective welfare of the three economies, discounted back to time zero, and the sum of the pollution stocks at T equals 50 are superior to the no trade outcome. While pollution is lessened and waste is recycled in the simulated economies, little can be said about whether or not these economies are becoming more sustainable without information on the proven reserves of the polluting resource. And since the use of the polluting resource is continuing and increasing, this model as constructed, provides no guidance on decoupling economic growth from resource use. It should be noted that the overall increase in waste stocks in the simulation with trade relative to the simulation without is an artifact of the specification of the waste equation of each economy. Because each of these equations is a balance equation, as costs of inputs are lowered, the rate of growth in waste increases by definition. Simulations with the present model then suggest that while it may be possible to reduce pollution with economic growth, waste handling remains a problem, at least in the case of this model. So, next steps in a research agenda. Of perhaps greatest importance in circular economy modeling of the kind we're considering here is the need to include a more process-based depiction of the generation of waste. Moreover, supply and demand for other materials used in production of gross output should be endogenized, and this can be done quite straightforwardly as presented in the paper. If the polluting resource were exhaustible, exploration for and extraction of the polluting resource might be represented by embedding Pindyck's model of these activities in the larger circular economy model. And in a paper published about 10 years ago, well, actually more than that, Clifford Weimer and I showed how you can estimate the nonlinear continuous time optimization problem of Pindyck using continuous time econometric methods. So eventually we may get to the point where we can calibrate or estimate from data the various parameters of a circular economy model. The activity of transporting resources and intermediate and final goods and solid wastes needs to be rendered explicit. So we need to have transportation networks and in which supply chain problems can arise, characterized for this to be an instructive approach to modeling the circular economy or the evolution to the same. Now, the handling of waste presents at least two problems for circular economy modeling. First, depicting how waste generation can be kept within the limits of the environment's assimilative capacity. And second, depicting reciprocal transport flows of waste going out while resources and materials needed for production come into an economy, thereby limiting non-point source pollution. If you can't do the latter, then you're taking a sticky object off of one hand and putting it on the other. Now, the models here considered are aggregate macroeconomic growth models based on heroic assumptions and simplifications. But the same could be said about Nordhaus's DICE model. Each of them can be seen to be somewhat instructive, but the real work in managing a transition to a circular economy must happen on a micro or meso scale, even as it's influenced by macro forces. In any event, further progress in understanding the structural transformations that will be necessary to transition to a resilient, sustainable, and more socially equitable global society will require research in which there is more empirical as well as theoretical analysis. These are the citations to which I alluded. And I want to thank you for your attention. And I will stop sharing the screen at this point so that I can entertain comments and questions.
Thank you. Thank you very much.
You're most welcome.
So I think we have a few minutes for questions.
Yes.
Is there anyone willing to? Yes. Get the mic. There.
Okay, thank you. Thank you very much for this very inspiring presentation. I find it very interesting, the results of your simulation, where you find that with economic growth, it is possible to reduce pollution, but not to solve the problem of waste. And so of course, you underline that this is a result of the balance equation. But what I wonder is the role of consumption. And particularly, I guess that also consumption may have a role in these results. And in particularly, my question is if at this level of abstraction, it means in this general framework, which is really very interesting from my point of view, because you show these flows, this original model when you have a lot of flow and stock that interact, and your extension is about international trade, and this lead to this good, let's say, results in terms of welfare. But the point is, if we change the way many consumer goods are produced in terms of improved durability, what can be the result? I mean, it is possible to mitigate these negative, let's say, results that you find. And this is, I think, important because even Kenneth Baldwin is in his article in 1966 remind us the importance of considering planned obsolescence and the low quality of goods, which of course has consequences in West generation. Thank you.
Well, these are all good points. And I should say that at a more micro level in specific industries, that the question of the durability and the other qualities that you mentioned, the quality of the goods in production, is being taken seriously. And we see in particular in the housing industry and in other building trades efforts to consider the design of buildings from cradle to cradle, so to speak, so that the materials that are being used in construction are being used with an eye towards how they would be recycled when the building's life is ended. Now, with respect to being able to substitute products that might be more durable or more environmentally friendly, we could help ourselves to some of the notions used by computable general equilibrium modelers who use what's called an Armington aggregate after Paul Armington, a former economist at the World Bank, who differentiated near substitutes on the basis of where they originated from and their relative qualities. And we could use some of the functional forms that he developed to represent that state of affairs in international trade models in this ilk of modeling, circular economy modeling. We would have to modify some of the notions, but I think the fact that there is substitutability between the different components would be a first step to recognize. And so I think we could pursue the question that you're raising here. And, you know, I admit that we have to do a better job of modeling waste, but I inherited that balance equation more or less from George and all, and I decided to stay with it to have a minimum deviation from the setup that they had developed. But thank you for your comment.
Yes.
Well,
Roberto.
sorry.
Roberto Scazzieri, go ahead.
Thank you very much. Thanks for your presentation. Two questions. The first one is the parameter sigma, the elasticity of substitution in your CIS production function, is not part of the circular cumulative causation set of parameters. So I was wondering, what is the role of this degree of substitutability between inputs of the CES production function in the results? Because I could think of a natural resource which is very difficult to substitute, for example, even in the long run, for example, critical raw materials needed for the green transition, that would require a Leontief type of coefficients, fixed proportions, because you cannot really substitute. as opposed to, for example, a service economy, where inputs are mainly tasks in occupations, and provided enough time is given, you could almost fully substitute one for the other by retraining the labor force. So what happens if your elasticity of substitution is close to a Leontief case? Would the results of this model hold? Or if it's very substitutable, then, as I assume it is in your case, because you assume a sigma of 1.05, that in a way contributes to the model to obtain the results. So would fixed coefficient pose any problem to the results you achieve in the model? Thank you.
Good observations. I assumed that the elasticity of substitution would obtain for all of the ingredients of the output equation, aggregate output equation, as a matter of convenience. And certainly in CGE modeling that we do, we have nested production functions where some of the inputs are fixed coefficient Leontief, and then they appear in higher level functions which do allow for substitution. So you're substituting Leontief aggregates for other factors. And certainly in an extension of this type of modeling, that should be done. And I would suggest even that partial equilibrium estimations of the technologies be done before constructing the modeling framework. But you're exactly right. This is not an accurate characterization of the substitutability between different types of inputs. And in fact, some may be stocks and some may be flows, and that needs to be allowed for as well. But thank you for your astute comment.
Well, thank you very much, first of all. I have a comment and a very short question. My comment is that, as you said, your model is based on aggregate assumptions. Now, there is, of course, there is a huge literature which is not an aggregate one, and also referring to the issue of circularity. Of course, there's I think, the paper which deserves to be well known by Vasily Leontief, who was already mentioned just a second ago by Arye Virkkerman, but I'm referring actually to Vasily Leontief's PhD dissertation, originally 1928, published in the journal Structural Change in Economic Dynamics, 1991, which is called The Economy is a Circular Flow. I think that paper is full of suggestions which cry for attention by current day modelers, actually. And I think it's quite interesting also from the current modeling point of view that Leontief already at the time was basically visualizing his circular economy in terms of what nowadays would be called graph theory. So this was just an aside. But in terms of what you have yourself said, which I think is extremely interesting, this visualization of increasing returns and learning by doing, and of course increasing return, learning by doing, increasing efficiency are all part of the same nested or connected set of ideas. Again, you would recall that there is an important paper by an American economist, Ellen Young, 1928, called Increasing Returns and Economic Progress, Economic Journal, 1928, in which the attention was called precisely on the roles of what nowadays we would call the architectures of connectivity in the generation of increasing returns, in the generation of increasing returns trajectories. So again, this moves back to one of your last slides when you said that there is a crying need to move basically the kind of research issues that you have addressed along disaggregated what you call meso specifications of the economy, which of course is closely connected with what we said right at the beginning of this workshop. To end my question times slash comment about recycling. Well, in terms of multi-sectoral approaches to recycling, I would like to mention the seminal work which was made by the last speaker to today's workshop, Alberto Quadriocurzio, who, using precisely a multi-sectoral and circular model of the economy, pointed to the possibility of phases along a dynamic trajectory of increasing returns, which actually seems to be very closely connected to what you have suggested. Anyway, it was just a comment and perhaps also a question about how do you think one should proceed in developing this cumulative causation model in a less aggregative framework?
Thank you very much for your comments. Let me first note that I was the beneficiary of your suggestions about the work of Leontiev and Young in an earlier iteration on the paper that was published in Networks and Spatial Economics, and I do indeed cite them and comment on them in the paper. Thanks for that. Thanks for bringing my attention to that. How to proceed going forward? I'm unfamiliar with the next presentation that's to be made, and will be excited to see how the author proceeds. I think, I think that it might be good to look at building up models of the circular economy for specific geographical locations. We have so many problems arising from sea level rise, the failure of infrastructure systems at the end of their service lives, housing issues, transportation issues, that we need to think about addressing those problems in the context of a circular economy. And I think that it's best to do that probably instead of adopting a global perspective or adopting a national perspective, to look at what a regional entity might be where that could be done, where we could work from the bottom up, so to speak. I know that the US NSF is now very concerned about promoting research from people from different disciplinary fields who come together to address what is a functional region and what are the characteristics of or the performance measures of a functional region, and what can we do to reinforce the positive attributes and mitigate the negative ones. So I would say we do need more of the inter-industry economics characterizations for which Leontiev is famous. We do need to embed that within the context of a phase transition type of model. But I think it also has to be grounded in a particular ecosystem or a particular environmental system which has specific problems that we're trying to address and which we can measure and monitor progress in those measures. So that's where I'll leave it. Thanks so much for your comments.
Okay. I suspect from the side of our warden that it's time to close, right?
Yeah, so if there are no more questions, I will try to keep the time.
There is a question.
Oh, there is another question, please. Yes, of course. Yeah, please.
Yeah.
I will take some time from the coffee break. Don't worry.
Just 1 second. Hi, Kieran. This is Roberto Patuelli.
Hello, Roberto.
Kieran, from what I understood, your model is non-spatial, right? There is no space, explicit treatment of space in the model.
That's correct.
Okay, so I was wondering, of course, for people in regional science like us, space is always considered very important. And if we talk about trade, which you introduced in one of the variations of your model, space matters for trade. And also for pollution, if you think, okay, of physical pollution like landfills, less. But if you talk about atmospheric pollution, of course, between contiguous regions, space is important because pollution moves in the air. So I was wondering if somehow space can be introduced in your model.
Well, certainly it can. If we go back to the earlier work of Walter Izard in the period of his career when he was working on spatial dynamic models. And in fact, I published a paper in 2001 on the solution and estimation of partial differential equation systems subject to boundary conditions to show how you could work with the kind of model that Izard was working with. Now, it was a very general model. It had the isoelastic utility function, and it had, maybe a CES or some other related production function technology. And it didn't have any of the things that we're talking about here about circular cumulative causation or involving recycling. But certainly, in his book on space-time dynamics, he does have environmental examples where pollution is traveling across regional boundaries. So I think Walter did some exploratory work in this area. I think that we have the tools to work with spatial data now. There are more than one econometric methodologies for working with spatial dynamic models. I believe that you've done some work in this area with labor force data. But there's nothing stopping us from introducing space to these kinds of models. I also published a paper in a collection edited by Art Geddes in which there are 2 dimensions of space. And so that's not beyond our means either. And it's also possible to embed the kind of model that I have here, but with spatial dimensions in a GIS system. And so you could be looking at 3-dimensional economies that are evolving over time. You could have a 4-dimensional GIS system in which time is another dimension. So I think the technologies are there. I think the know-how is there, but I think it requires the coming together of people with appropriate understandings of environmental science, engineering, data analysis, certainly economics. And I think there's a bright future for work in this area, and I think space can be integrated, if that's the answer to your question.
Thank you. Thank you very much. I would like to thank the speaker again for the questions and the seminar.
Thank you, Kieran. Thanks a lot.
You're most welcome. Thank you.
Yeah, I want to thank you. And also now I want to apologize because we are going to a coffee break, but this is not something that we can do virtually. So we cannot offer you a coffee, but we hope to see you soon in Bologna. And I suggest that we move to the coffee break. I suggest we try to catch up time. So I said that we convey here strictly in 23 minutes from now, so 4:40. It means only 10 minutes beyond schedule, and then we will try to catch it up. So the coffee break should be here. And thank you again for your attention.
I have to ask for your forgiveness. I have to leave for another appointment that was booked before I was asked to present at this, so I will be missing most of the afternoon session. But thanks anyways for including me.
Thank you for being with us. Thank you.
Thanks a lot. Thank you.
Okay. I will start. Thank you. Hello. And I'm happy to start the section 3 with our guest that it will be introduced, Ariel Wickerman. I also would like to have here Dr. Thanks Ivano Cardinale from the University of London. And for some introduction, we also have Professor Patrizio Bianchi from the University of Ferrara. I think he has some experience about policy making in complexity framework. He has been, for people who doesn't know, assessore regionale here in Emilia-Romagna, but also National Minister of Education of Italy So he knows what are complexity framework, he knows what is policy making. So I'm thank him for first of all to be here, and I leave it the floor for the introduction. Grazie.
Thank you so much. Thank you so much to everybody. Let me thank you, Roberto, for this very kind invitation to say something in this extremely interesting forum. Let me say that I am so lucky to have the possibility in my life to play on one side as university researcher and on the other side as you say, as policymaker. But let me say that in my experience of policymaker, most of my activity was devoted to create networks. What is that, a network? A network is a number of actors, people, companies, schools, universities, regions, states that decide now to have special relations among them, to create connectivity, to create something new where everybody say that it's possible to reduce its own freedom of movement in exchange of an increasing of collective interest. The first issue that I faced in my activity was to create a sort of identity of this network. The network is working, it have an identity. If the people, the companies, the universities, the actors that decide to say part of a network, they identify themselves in a collective interest. When we are putting on the table the question that Roberto put on the beginning, at which extent theory can be the base of an adequate policy making, I think that this is the first element. We can have probably natural networks, but network is not a tendency to merge different subjects in a new subject. It's not a merger. It's not, on the other side, a more or less a casual convergence on a specific issue. Is a policy. Is the capacity to build up a structure that is able to pilot the structural transformation, the structural change of the relations. For this reason, in terms of policy making, I don't believe that we are just looking for an optimal final state. There is no optimal final state. This is obviously is a part of model. But in terms of policy making, don't forget it. There is no optimal final state because there is no final state. We are working in a context of structural change and economic dynamics. And networks are relevant because they are a way to pilot the economic dynamics in order to generate a transformation of the structure of the economy that is sustainable by the society. Not all the structural changes are sustainable. Revolution means that we are not able to pilot the transformation. We have a cracking, and from this cracking of the different molecules, we are regenerating new completely order. When we're speaking about networks, don't forget it that we have different models of analyze the process. One is just in the model, in the economic models. But when you are working in the reality, we don't have a starting point, a final point. We have simply the capacity to enter in a situation, in a historic situation, and to try to intervene in order to induce the people to generate a strong new society, a strong new aggregation. And you have to decide if you are able to maintain open this aggregation. Time by time, the situation is so complex that I can understand that the first attitude is to close the system, to oversimplify the system, to reduce the complexity of interaction simply to a vertical structure under the command of the stronger subject. But when we are speaking about networks, we are speaking about a living subject. And we have and we need to work on the old concept stated by Adam Smith. You remember in The Wealth of Nations, Smith said quite clearly that collective efficiency is not given by individual specialization, but is specialization of the individuals plus collective complementarity. Complementarity means the capacity to understand better which are my own specialization, my own capacity, my own skills, dexterity, and judgment, as we say, Roberto, you remember, but also to understand better which are the skills, dexterity, and judgment of all the other people that we are generating an interaction. To create a network, we need not only a capacity to research our own capacity, but to be able to understand also the condition of the others. But this is a dynamic process. Complementarity searching is a dynamic process. Is the element making dynamic the system, is the element making dynamic the network. Otherwise, we have just a closed system. And biology is teaching us that all the closed systems are determined to die. In this system, I feel that is extremely important what we are studying today. In my understanding, the work that we are doing today on connectivity is crucial. Connectivity is not just a relation. It's not just a casual relation. It's the capacity to build up stable but dynamic relations in the future. But this means the capacity to look inside the future. Connectivity is not simply a state. Connectivity is a dynamics, is a structural dynamics. For this reason, let me come back to the main question that Roberto put at the beginning. At which extent the theory can be help the policy making? Depends. Depends which kind of policy making are we looking for. Theory can be supporting the idea that we are just looking to a final optimal state where everybody must be simply on the same line. Or on the other side, I believe that what we are doing, looking in this analysis that we can call structural change in economic dynamics, that we have to create contexts which are open, inclusive, and I feel also dynamics because they are explicitly democratic. In this sense, I think that we have a lot to work together. Thank you.
Thank you, Professor Bianchi. In physics, the connectivity we call the interaction and this kind are very, very complex among policy making and all the actors involved. And I agree with you. Thank you for your word. I want to give a word to Ivano, but first let me welcome again our speaker, And I just want to mention about your paper that I know very well who is Markov, but I don't know the other guy, so I will be very curious about it. Please.
Well, Ariel is the perfect person to tell us who Leontiev is, so we are in luck. No, I just wanted to introduce our speaker. So we are delighted to have Dr. Ariel Virkierman as a speaker in this session. He's a senior lecturer at Goldsmiths and a colleague in the Structural Economic Analysis Research Unit there. I think it's especially well suited that Ariel is our speaker in this workshop because connectivity, especially in the input-output sense of it, is at the core of how he sees the economy. And on that basis, he has developed what I think is a unique profile in terms of consistency and range that goes from the historical development of circularity in economic thinking to theoretical work on multi-sectoral model to developing new empirical approaches to study global interdependence, and he's also worked in policy areas, for example, advising ECLAC at the United Nations. And one project of his that I want to mention, because it's particularly relevant in a policy session, is on global value chain restructuring from the point of view of competitiveness, productivity, and strategic trade. So, Ariel, you have the floor.
Thank you. I hope you can hear me. Thank you, Vano. Thank you, Professor Bianchi, for your presentation of the session. Just want to check. I have 30 minutes, more or less. Yes, okay. So thank you very much to the organizers for inviting me. It's a privilege to be able to speak on Leontiev meets Markov, sectoral vulnerabilities and policy implications. A brief outline of what I'd like to speak about. Who was Leontiev and how analytically he can meet Markov has to do with connecting inter-industry interdependencies, so the relationship between productive sectors through input-output tables and the analytical device of Markov chains. I would try then to explain why we can define a betweenness centrality measure that works as a vulnerability gap at the local level, at the level of individual sectors of the economy, and defining an empirical transition probability matrix will be crucial to understand how different sectors in the economy, including final sectors of the economy, are related to each other. I will briefly detail the empirical strategy and the results we obtain. And finally, I'll try to draw some policy implications. So to begin with, this presentation is based on the paper that was published in the special issue of Networks and Spatial Economics, which gives rise to the workshop we are working, and its joint work with Professors Monica Bianchi and Anna Torriero from the Catholic University in Milano. The idea is we have this device called an input-output table, which is a matrix, so two-entry representation of the bilateral flows of commodities in terms of monetary units between industries. That means that on the rows you have the industries that will be supplying inputs, and on the columns the industry that will be demanding the inputs in the economy. So each of these cells will represent a structural interdependence between two sectors in the economy. So you can see this is a device that was introduced already in the 1930s. And in the picture, you can see how in the 1950s, it was a very popular device for economic planning in the US when working with indicative planning and planning for different functions within firms and for the whole economy and within government. Now, the idea is that this device can be seen analytically as a Markov chain. A Markov chain is this chance process interpretation of the emerging connectivity in the network. So for example, if we have this very simple network consisting of 3 nodes, it can be represented by this matrix. And the idea is that each iteration of the network implies a specific traversal of nodes through the system. For example, if we start with the first iteration of the network, we have that once one node, node 1, will have with probability 1 the transition to node 2. In the next iteration, we will start from node 2 and it will have half and half probability to traverse to nodes 2 and 3. If it traverses to node 2, then again it will start from node 2, where if it traverses to node 3, then the next iteration will start from node 3. So the idea is that this is an iterative process that describes the connectivity of a network, and what allows us to do is to understand the systemic importance of different nodes in the network based on the pattern of connectivity. Now, Leontiev and Markov may have never met. Maybe they never met because by the time Leontiev started his undergraduate degree in St. Petersburg in 1921, Markov was leaving the university, retiring from the same university in 1920, 1921. So probably as a first-year student, Leontiev never managed to take one of Markov's courses, but they almost coincided even at the same place, but probably they never met. The idea of Leontiev meets Markov is putting an emphasis on how the input-output table can be seen as a weighted D-graph, that is, as a weighted directed network. This idea is not new. It has been present since Solow and Morgenstern in the 1950s. But what is relatively new is how this input-output table and the model can be related explicitly to the language and tools of network science. This emerging paradigm of complex networks to understand how connectivity, vulnerability, resilience can be understood and analyzed. And there are some recent contributions that try to put the input-output model into this context. A key difference emerges when we consider what's an open with respect to a closed input-output model. In an open input-output model, the final uses of the economy, consumption, investment, are seen as autonomous, and any money spent on them are seen as autonomous injections. And the primary costs of the economy, the income in the economy, is seen as a leakage, as something that will leave the system, not re-entering the circular flow of commodities being produced by means of commodity. On the contrary, a closed input-output model has a complete circularity in the sense that wages will be the source financing consumption, profits financing investment, and taxes financing government expenditure, imports financing exports financing imports, and so on and so forth. So there will be a complete circularity in the system. Now, the relevance of this contribution and the antecedents. Already in the 1970s, Kemeny and Snell already mapped an open, not a closed, an open input-output system into an absorbing Markov chain. So they see this isomorphism, this equivalence between these two analytical devices. Only that by being open, they needed an absorbing Markov chain. More recently, a group of economists and physicists devised some set of centrality measures based on random walks on graph to interpret the propagation of supply shocks through the industries in the economy. And they also were working with an open input-output system. And the shocks they were considering were shocks departing from the primary inputs of the system, from income leading to then all the industries in the economy. What we do in this paper is to map a closed input-output system. So when we talk of a closed input-output system, we talk of a system where circularity is complete into an ergodic regular Markov chain that will have three final sectors. And this is very important for the policy implications: a foreign sector, the households and government sector, and a profits and investment sector that will be connected in a circular way. And then the traversal across sectors of a random walk will allow us to measure the sectoral vulnerabilities of each sector in the economy using a measure of betweenness centrality. I would like to devote a couple of slides to the mathematical structure of the paper, but I won't stop a lot on them. So if you have any questions, please feel free to ask me afterwards or interrupt me for clarification if it's allowed. So we start from a matrix that will represent each cell of this matrix, the strength exerted from node I to node J. This is a simple weighted D graph. Yes, the relationship between two nodes. Then we define the out strength, that is the total strength exerted by the node in a row, and we define a transition probability matrix that will allow us to define a Markov chain. Now, if we have a strongly connected graph, by strongly connected, I mean that between any two pair of nodes, there will be a direct or indirect path that connects them. So this allows us to define a graph that is strongly connected, the matrix that results will be reducible, and the Markov chain will be regular. In this way, we can define the stationary probabilities that will give us the systemic node importance of each sector in the economy. That is the idea of the long run proportion that each node, that the random worker will spend on each node of the economy. That will the long run average proportion with which a node that is a random walker that is circulating will spend on each of the sectors of the economy. But besides this P matrix, we can define what's called the graph Laplacian matrix that will give us important information in terms of the degrees in the diagonal, in this case, the stationary probabilities in the diagonal, and it's quite useful for several graph properties. In particular, if we compute the Moore-Penrose inverse of this asymmetric Laplacian, and the Moore-Penrose inverse can be computed by singular value decomposition, and we would obtain, it's a kind of more general inverse matrix. This Moore-Penrose inverse, the elements of the Moore-Penrose inverse allow us to define what's called the mean first passage time, which will be the expected number of transitions that we need to go from one node to the other. So how long it takes on average of this random walk circulating, starting in node I to reach node J. So once we compute this mean first passage time, the idea of how long it takes to go from one node to the other, we make a comparison. We compare this unrestricted time it takes to walk from I to J with a restricted path that consists in being forced to walk from I to J, passing through a third node, which is K. And so the idea is, if I have to pass through node K, then the mean first passage time that is constrained will consist on going from I to K and then from K to J. So I need to split my path into subpaths. And what can be shown is that if we take the difference of this constrained path with respect to the unconstrained path averaging across nodes, what we get is a measure of betweenness centrality and vulnerability. Why? Because on the first term, we have the average length of walks restricted to pass through K. So imagine you have a sector in the economy which is really peripheral and far away. Then if for any sector in the economy, so if you need to go from glass to construction, you need necessarily to pass by a third sector, which is very peripheral, for example, a health service, then it will take many iterations for glass to reach construction if it has to pass by health services. Instead, if you have a node which is key, for example, energy inputs, yes, energy consumption in the economy, then almost every path that is undergoing this random walk will pass by the energy input sector. So as a consequence, we will have that if the difference between the constrained path and the unconstrained path is very large, that sector will be very peripheral. If it's very small, it means that any node I will frequently have to pass by this intermediate node K to reach a third node J. And this extra distance traveled between any node pair, when forced to pass through a given node, will give us the betweenness centrality, this communication control that node K has over the others. And this can be understood as a vulnerability gap. Why? Because if we have a very central node in terms of its betweenness centrality so that any path going from I to J needs almost necessarily to pass by K, and we remove this node in a target attack to the network, then we will be disrupting many paths in the network, and that will probably create a big vulnerability to the network. So the idea is, why is this betweenness centrality indicator important? In a very simple example, if I take a simple network consisting of these nodes and starting from 1, 2, 3, 4, 5, 6, 7, these 7 nodes, and this is the W matrix. In this case, it's unweighted, but just for exposition, but you can also generalize it to any weighted the graph. You define the probability transition matrix. You can compute the systemic importance of this network, of this Markov chain, and the systemic importance will be the left eigenvector associated to the maximum eigenvalue, which will be the unitary eigenvalue because of the properties of the matrix. And if you look at systemic importance, which intuitively tells you how important I am in terms of how connected I am to important nodes. So my importance depends on being connected to important others. Yes, this is the notion of systemic centrality. Instead, and you can see that in this network, the systemic centrality is equal for all nodes. Instead, the betweenness centrality is very different. There is a clear hierarchy in the betweenness centrality. Why? Because if you take node 4, we'll have a value of betweenness which is very small. Why? Because in order to connect the two parts of the network, the one between nodes 1 to 3 and 5, 6, 7, if you remove node 4, there is no communication possible between the two parts of the network. So in terms of betweenness, node 4 will be the most crucial. The same happens in this hierarchy. Then you will have the nodes that are very close to 4, and finally the nodes that are further away from node 4. So you can see that there is a rationale for measuring the vulnerability in terms of betweenness centrality rather than systemic importance. What will be the P matrix, the probability transition matrix of our exercise? We consider a closed input-output system. And by this, what I mean is a system where you have an expenditure circuit, where you have intermediate inputs, final output, and primary incomes, and they will be related by these systems of equations, dual system that determine quantities and prices in the economy. You can express the system in terms of gross output, in terms of units of gross output of each buying industry. So if I consider a column of this matrix, I divide by total output, this lowercase x vector, each column. So I would be post-multiplying a diagonalized matrix with the inverse of this vector. And what I would get is this set of structural coefficients matrix, A matrix, that will contain the interconnection between intermediate sectors of the economy with this A matrix, the propensity to spend out of income, and the requirement of primary income for each unit of output, of gross output. So this structural coefficient matrix is quite useful for our purposes, because this matrix, when we transpose it, we get an, if the matrix is non-negative, so there are no negative elements, irreducible and row stochastic, in the sense that summing across columns for each row, we get 1, and this will be the case with empirical system, provided some mild conditions, then this structural coefficient matrix can be interpreted as a probability transition matrix of a Markov chain. And the meaning will be that any coefficient inside this AT matrix will tell us, each Pij will tell us the payment from sector E to sector J for the inputs per unit of output. And here duality is very important, because at the same time there is a payment from I to J there for each unit of output, that sector I is selling to sector J, there will be a delivery of commodities from sector J to sector I. So we have this dual nature of the transactions. We are following the flow of money. We could have followed the flow of commodities, but by transposing the structural coefficients matrix, we follow the flow of money that takes place in the system. And you can see that there are payments between productive sectors. There will be payments from a sector to the final sector as a cost component. So productive sectors will pay wages, will pay profits, will pay for imports that are not produced inside the domestic economy. And then the final sector will spend that income into consumption, investment, and exports. So what is the rationale for interpreting? Because we can formally do this exercise, but does it have any economic meaning? It does. Already in 1970, this Hungarian economist called András Brody introduced a very clear rationale of how we can interpret a closed input-output system as a Markov chain. Because the idea is that one sector, the quote says, will go to the market and will buy one day from one sector, another day from others. The purchases may have an apparently irregular pattern. Some days it may not buy anything because inventories are full, to be depleted and random. Nevertheless, the probabilities of spending will be allotted to other sectors as the coefficients indicate, and the real frequency of purchases followed through, for example, an accounting year will approach this probability. So this is the economic logic of why we can see an input-output system as a Markov chain. Now, this is a very simplified representation of reality. How can we fit this theoretical representation to the complication of actual input-output data? Actual input-output data have many intermediate sectors, but also many final sectors in the economy. So what we did in the exercise is to create three final sectors. One which will represent the foreign sector, imports and exports. So in terms of the row, you will have all the imports of products by intermediate industries and final demand. And then we have on the column the structure of exports, yes, how any productive sector will export to other countries. Then we have a households and government sector that will essentially put together the activities of households and the government in terms of income as regards wages and taxes, in terms of expenditure as regards private consumption and general government final consumption. And then we put together a profits and investment sector that on the side of income, it will contain the gross operating surplus, so essentially profits in the economy. And on the side of the column will be the gross fixed capital formation, which is the investment that increases productive capacity in the economy. So by making this mapping, you can see an illustrative example for the economy of the US in 2015. What you can see is that you will have the intermediate block and then three final sectors, the foreign trade, the consumption, and the profits investment sector, where the key here will be how imports will be connected to exports, consumption, wages and taxes will be connected to consumption, and profits will be connected to investment, in the same way as then each sector will be connected to each other sector. We can turn this into a set of symbols, and we can then define this income system in intensive terms, transpose it, and obtain this non-negative irreducible row stochastic matrix that will be our empirical transition matrix. Why is this transition matrix relevant in terms of the insights it can provide for policy? For this is, I think, I believe, the key contribution of the paper conceptually, and it runs as follows. These three final sectors will be the most important sectors in the economy. Intermediate purchases will be a minority of the total value of output in the economy, whereas the final sector will probably be more important. Consumption is a greater share of income rather than other components of the economy. So the idea is that if we consider imports, this second column, each time a random walker arrives and needs to import a commodity, our imports become income of the rest of the world that at some point will be spent into our exports. So when they buy our exports, then they will buy the exports in proportion to the distribution of exports of the different productive sectors. Now, what happens is the following. Imagine you have an economy, a small open economy, which has high import participation in the cost structure. So sectors will very frequently hit on needing to import commodities. And then that will become an income that will become exports, income of the rest of the world that become our exports. If the country, this small open economy, has a very concentrated export structure on very few sectors, that will mean that there are few possibilities for this random walker to reach productive sectors again. Instead, if our export structure is very diversified, then there is a higher likelihood that you can reintroduce circularity to the productive sectors if your export structure is very diversified. The same happens with profits and investment. If you have a very concentrated structure of investment, so that, for example, most of the investment in the economy goes in the construction sector because you have a housing bubble, and little investment goes towards plant capacity and fixed capital machinery, advanced machinery, or intellectual property products, so intangible capital, etc., then what happens is that whenever you hit the profits element of income, that will become investment in the next iteration of the Markov chain. But what may happen is that if investment is very concentrated on few industries, then there are bottlenecks to then go back to circularity again, because all profits will go to the construction sector rather than be distributed among many sectors of the economy. And finally, the wages and consumption part of income, when they become consumption, given that it's the highest cost element, the fact is that it's very important, the structure of final consumption demand, to understand how circularity will be distributed across productive sectors of the economy, because more often than not, the cost structure of industries will reach wages or taxes, and then that will become consumption, and how distributed consumption is in the system in terms of its relative structure will allow us to then see if productive sectors are reached fast or slow. So what we do empirically is we take a time series of input-output tables from the OECD for a decade between 2005 and 2015. And what we try to do is first assess the time trend of the ranking of these sectoral vulnerabilities. We compute this M indicator, yes, the one we have here, this vulnerability gap. We compute it for 60 countries throughout 10 years for a set of economies, and we rank them according to the decreasing order of between centrality, so as to identify the most central with respect to the most peripheral nodes of the network. And we try to see whether there are first differences through time, whether there is a time trend in the evolution of these sectoral vulnerabilities. Then we try to confront cross-country differences, contrast cross-country differences in sectoral vulnerabilities, whether the sectoral vulnerabilities of China are different from those of the US. And then we perform a clustering exercise where we agglomerate countries based on the similarity of their sectoral rankings. So very quickly, the problem here is, as always with displaying input-output results, is that we have many sectors. We have almost 40 sectors, and it's very difficult to zoom in. So what I would do is comment on the results. But if you want to read the results in full, please go to the paper, and hopefully you can zoom in and see the graphs more neatly. Essentially, when we look at the extra distance traversed between two sectors when forced to pass through the sector J, the one we are computing the centrality on, and we compare 2005 with respect to 2009 and 2015, what we get is a very stable ranking at the very top and a lot of movement from the mid part of the ranking to the bottom. What does this mean? The fact that there is a high persistence in the centrality of sectors has to do with, I think, 3 points. First, the most central sectors are the final sectors: consumption, profits investment, and foreign trade. Then we have consumption, we have a set of infrastructure core of the economy: construction, trade, knowledge-intensive business services, logistics, energy, finance, and then we have a final consumption set of industries: food, housing, government services, health, and education. Those are the consumption and production infrastructure core of the economy. They are always the most central sectors. Instead, the second half presents more variability. You have more switchovers in the ranking. You have productive techniques that change faster than the essential infrastructure of consumption and production. And you can think of it as follows. You can see, for example, the metal industry is going down in terms of centrality. Why? Because probably the metal content of cars is going down, but the need for mobility and for transportation is still very important. So you can see that production techniques change, but the social function that these commodities are put for stays very relevant. And the second reason why sectors at the second half will move has to do with international fragmentation of production. You will see that sectors like textiles, computing, they change their position in the ranking. And this has to do with the fact that we are considering domestic economies. So what happens is that when there is international fragmentation of production, the sectors will reach imports faster because we will be importing more inputs to produce our output, and the centrality of sectors that used to be more intensive, produce at home, will now reduce their intensity. So what you can see is that central sectors become more central across most countries, and peripheral sectors will become unevenly more peripheral according to the country. So there is a phenomenon of convergence at the top and divergence at the bottom of the betweenness centrality distribution. Then we can take cross-country differences. We can time average our results, and we can compare how central sectors are between different economies. And in this graph, you have the centrality structure of China, the medium world economy, and USA. And what you can observe is the movement in the centrality when confronting China with respect to, for example, the US. This has to do with the changing sectoral vulnerabilities along a development path. And you can see how when you move from China to the US, you can see how agriculture, food processing, textiles, metals, mechanical machinery become less important. So they are very important in China, less important in the US. And this has to do with China undergoing a process of industrialization and population growth. Instead, when you look at the US, you will see an increasing importance of real estate, knowledge-intensive services, IT services, so technologically advanced personal services and finance. So you can see how transitioning to a service economy changes the vulnerability structure of the economy. So this you can do for any pair of countries that you want. This is just an example. And finally, what we did was we take this difference in the similarity in the structure of centralities across countries, and we perform an agglomerative hierarchical clustering. So we cluster countries according to the relative distance in their sectoral rankings for our betweenness centrality. So that what we would do then is to group countries according to how similar they are in the structure of their centralities. And you can see that one can, in an heuristic exercise, identify 6 different clusters. These clusters I believe they are quite interesting because they show us 6 different profiles of or types of economies that you can find in the world. First, the first group contains mostly Asian countries. They are Factory Asia. They have very central sectors related to global value chains, such as textiles and computer parts. They have centrality of sectors related to population growth, such as food processing and some natural resource exploitation, which is central to these Asian economies. And well, some other like Mexico, etc. They are economies that are very integrated with international fragmentation of production. Then the second group has some middle income economies where construction is very central and they are far away from the technological frontier because high-tech industries are very low in terms of centrality. Then the third group comprises a wide range of economies that, if you look at them carefully, includes Russia, Brazil, South Africa, Norway, Australia. They are all natural resource-based economies where mining, petroleum, agriculture, food processing are central. Then you have a fourth cluster, which comprises a core set of manufacturing-intensive economies in Asia and Europe, where heavy industry and high-tech manufacturing is crucial. The fifth cluster, which contains mainly service-based economies, advanced service-based economies, and the sixth cluster, which includes, for example, Italy, is a set of European countries based on services and traditional manufacturing sectors, which is slightly away from the technological frontier. So this type of analysis allows us to see, in a way, the structure of the world economy in terms of how central sectors are in terms of this betweenness centrality. So some policy implications, and with this I would like to conclude, that we can derive from this type of results. First, when we consider trade, industrial, and innovation policies, the commodity composition of exports, final consumption, and investment will shape structural sectoral bottlenecks of circularity. When I was discussing the fact that if you have a very concentrated structure of exports, then this will lead to a set of very peripheral nodes in terms of other industries. Why? Because you can only reach the productive sectors through a very limited set of exported commodities. These results could be useful for counter-cyclical business trade cycle policy framework. Why? Because we could simulate targeted attacks to different nodes in the network according to their betweenness centrality and see how the distribution of sectoral vulnerabilities change. And in terms of the results we obtained, what we got is structural change takes time. You can see that the first half of the ranking was very slow to move. And this means that we need policy persistence as a necessary condition for structural change. Countries will change their sectoral vulnerabilities along the development trajectory. And this means that policy will need to adapt or even be the engine of change if we want to transit from China to a structure similar to the US. And then the country typology of the profiles of sectoral vulnerabilities shows that we need nuanced vertical industrial strategies. A one-size-fits-all will not work because countries have a different sectoral strategy, a different sectoral structure of vulnerabilities. Thank you very much. Thanks for your time, for the time.
Thank you, Ariel. Thank you very much. We have short time for a quick questions, if there is any. Professor Bazzani, Armando, quick question, quick answer. There is already a question.
Just for maybe a bit technical, but my question is the following. For computing between centrality, we use the standard, the best path. So I take one node, another node, and then I take the best path according to the number of link I need to connect the two nodes. You take the average length for a random walk. There is some difference, you expect some difference in between centrality computed with best path and your between centrality?
Thank you. Clearly, they Thank you for the question. I don't believe, given that we work with weighted digraphs, I believe we consider all paths rather than the shortest, the path with the minimum flow that you would consider if you were minimizing the distance between any two nodes. We use that metric because essentially we believe that otherwise we would be disrupting the normal structure of the system, in the sense that we are following the path that industries use to purchase from each other. So if we were forcing the path to go through one industry or another in terms of reaching a third node, it would amount to planning the set of purchases that the random worker is doing. And we know that in the types of economies we consider, industries plan their purchases in terms of their probabilities, in terms of their cost structure, rather than there being a central planning trying to minimize the flow between the different sectors. So we could call it a type of positive analysis. If we were willing to do a normative analysis where we want to minimize the flow of purchases between the distance between any two sectors by buying through the sector that is closest to a third sector, we could try to use geodesics, right? We could try to use minimum paths. Yes, thanks for the question.
Thank you, Ariel. Thank you again for your answer. Any other questions or comment? Please.
Thank you. I have two comments, one question. The first one is, we know about this literature on economic complexity, relatedness, and in some way it seems that vulnerability is that has something to do with low complexity, but I'm not sure if there is some connections between these two approaches. But the second question is, this framework, we know that in Europe we have these unbalances even at the regional level, with growing areas related to strong concentration of manufacturing activities, and probably we know that there is something related to international supply chains that has a sort of organization. Do you think that this framework can be used to understand more on the empirical ground how is the organization of such distribution of economic activities within Europe?
Thank you very much for the relevant comment and question. As regards the comment, yes, I fully agree. This type of literature should talk to or connect with the literature on economic complexity. I haven't done so. I started exploring it. Essentially, your observation that high vulnerability might be related to low complexity, I find it an interesting intuition. I would need to think more about it. I can say that from the framework of this relatedness framework, the framework of related diversification, the fact that economic development takes place by jumping from industries that are very close to the industries in which you specialize, is something that can be operationalized in input-output terms. We can think of the relatedness between two industries by, for example, computing the cosine similarity between their input structures, so that two industries that are very close means that it will be simpler to jump from one industry to the other because they have a very similar input structure, and that would mean that the industries are very related. And in the same way, we could analyze the output structure to see how industries can be inputs. Supply to industries are more or less complementary, but it should be something that needs to be explored more. And as regards the question of whether this type of framework can offer some insights on the effect of unevenness in the distribution of spatial distribution of economic activities in Europe, I believe it could. One would need to take regional input-output data and implement a similar framework and see which are the structural bottlenecks at the regional level, maybe extracting regions and try to see how the whole system reacts to that. And it could be done. Computational power there needs to be, because we would be talking about there exist, but these matrices are much larger. So then with normal computing equipment, it's more difficult to do all the computations. One important element computationally of the contribution is that normally this betweenness centrality, instead of being computed using the Moore-Penrose inverse of the asymmetric Laplacian, is computed by doing what's called the absorbing chain technique, by removing one row and one column and computing an inverse. So in theory, our approach allows us to also gain in computational time. But of course, if you have very big matrices, it's a challenge to then compute all the magnitudes. But thanks, it deserves to be explored.
Thank you, Ariel. Thank you for your last answer. If there are no more questions, I will thank the speaker again. Thank you. And I will move immediately to the last section because I'll be late. We are a little bit late. I will ask Professor Carlo D'Adda to join us and eventually introduce the next speaker, which I hope is still connected because we are a little bit late and I apologize. And then I will also ask the organizer to come here now or later to conclude the workshop. Sorry? Okay. I thought you were going to introduce him. Well, I'm going. So let me check if Professor Alberto, but you can join us. Alberto Quadro Curzio is still connected. I don't have a title of the presentation, but I'm sure he will be able to speak by himself. Over there. I think I see him. Prego. Alberto, you must turn on the microphone. Devi accendere il microfono e provare a parlare.
Alberto, mi senti?
Mi sentite adesso?
Sì.
Bene, grazie. I will be very, very short because I have another meeting at 6 o'clock and I have asked Carlo D'Adda to leave me. Do you hear me? Yes or no?
Yes.
Good. So, Carlo, many thanks for having
Alberto, mi senti?
Sì, io ti sento, e tu?
Bisogna dare...
Bisogna dare che cosa?
Professor Curzio, ha dei lucidi? Sono quelli che vediamo? Parlo in italiano per agevolare.
Allora, io parlo come vuole lei. I lucidi li ha lei, non io.
Sì, ce li abbiamo, tutto bene. Ci pensiamo noi coi lucidi, perfetto. Lei...
Appunto. Allora, thanks.
Mi scusi il ritardo.
Thanks to Carlo D'Adda, who gave me the possibility to speak before him, and thanks to persons or professor who organizes this meeting, Cardinale, Reggiani, and Scazzieri. Unfortunately, I have only 10 minutes for my short speech, and so I will do my best to explain what I would like to explain, even if it seems to me more or less impossible. Would you go to the second slide, please? No slide. Second slide. I start with an Italian statement. The economic theory is useful to understand, to hypothesize the future and to program the future. Reality and history request the control of the theories. In economics, institution and technoscience are crucial for any kind of project. Altra slide, per favore. I just put here two books I wrote many, many years ago, in which I try to explain how the dynamic of a system, a multi-sectoral system, might have discontinuities due to the lack of natural resources. And these discontinuities usually brings a period of transition to other technological system, which takes often long times. Terza slide, per favore. This book has been translated and widened in another book with REN Resources and Technologies, written by myself and Fausta Pellizzari. The crucial point of this title and the previous title are resources and technologies. Rent is a consequence of the relationship between resources and technologies. Other slide, please. I think that everyone is interested in the economics, or better, sorry, political economy, in which most of us have worked along many years, should go through this dictionary, the Palgrave Handbook of Political Economy, which seems to me a kind of Bible for all people who are interested in political economy and not just in modeling, or worse than that, just with the fight in the markets. Go on, please. In 2001 possibly, Fondazione Edison, of which I am president of the scientific committee and Marco Forti is the co-president, organized a conference, international conference on complexity and industrial clusters, dynamics and models in theory and practice. And the conference was opened by Murray Gell-Mann, Nobel Prize for his discovery on quanta, who wrote a very important essay, What is Complexity? This is just an information, but an information which means that 24 years ago, this topic was already clear to someone who are, in a certain way, a member of the so-called community of structural dynamics. Murray Gell-Mann was inside this discussion. Of course, he was not a political economist, but he explained how complexity might be useful for structural political economy. In a certain way, this is my interpretation and interpretation of Marco Fortis, who wrote with me the preface of this book and some chapters of the book. Go on with the slide, please. Well, this is just the slide of the book with all the participants, but it's not so important. It's important to point out that this book was being elaborated in 2020, which means more or less 24 years ago. Go on, please. I am going to conclude, even if I have about 20 slides. The G7 of Science Academy, which will be held in Accademia Nazionale dei Lincei, Corsini Palace, on March 2017, had one of its statements with this title, New Economic Growth, the Role of Science, Technology, Innovation, and Infrastructure. I chaired this session, and I wrote more or less the statement. I couldn't put in the title the definition which in my opinion is behind all these: structural economic dynamics and structural changes always along the path of growth, due also and in some cases crucially by the natural resources boundaries. Go on, please. Well, this is the statement. Everyone can find it on the website of Accademia dei Lincei, And the statement, of course, was signed by the president of the 7th Academy of Sciences of the G7. I think this is very important because the only economist there was myself. I was the only one. But all the president understood the structural dynamics is very, very important also for the discontinuities of technological innovation and scarcity of national resources to understand growth. Go on, please. Along 24 years, Fondazione Edison with Accademia Nazionale dei Lincei elaborated more or less 15 volumes on the relationship between technosciences and platform, but the so-called background of all these publications from the political economy point of view was structural dynamics, innovation, discontinuities, and all these things. That is what, in a certain way, is a paradigm of structural dynamics from a political economy point of view. Go on, please. Well, I don't explain this slide, but I just quote two fundamental platforms for organization of science, taking into account innovation and structural changes in the growth of the economies, system, interrelationship, structural change. I put here CERN because it is the biggest platform in the world, which has to do with nuclear research for peace aims. Go on, please. Go on, please. Go on, please. Well, it's impossible to go on. I had another example. Do you hear me?
Next.
No. Do you hear me? Yes. Go on. Another structural, fundamental platform is the European Molecular Biology Laboratory, which is in a certain way the twin brother or sister of CERN for the biological research. I cannot go deeply in these topics because it's too late for me, but what I want to stress is the relationship between structural change, technological innovation, transition path from one structural system to another structural system, and the relationship with scarce natural resources are fundamental. Many thanks for your patience. I have been too quick, but unfortunately, at 6 o'clock, I have to leave the meeting. Thank you to organizer, Cardinale, Reggiani and Scazzieri, and thank you to the chairman of this session.
Thank you very much, Alberto.
Prego, a presto, scusate, ma devo andare.
Thank you, Professor Curzio, for your short but interesting talk on innovation, structural dynamics, and discontinuities. I don't know if there is any comment or questions, but more general, I would like to invite the organizer, Aura, also, if you join me, so we can finish the... Oh, yes, of course. And then I will give the floor to Professor Dadda for the last speak, and then we are going to the closing remark. Thank you, and thank you again, Professor Curzio, for taking your time to be here for us today.
Goodbye.
Please, Professor Dadda.
Okay, thank you very much.
Thank you.
My talk will be very short. So if you want, you can consider it at, say, a goodbye closure. I think that to an economist, the phenomenon of structural change that has been taken place worldwide over the last few decades is certainly well visible. Useful data to describe this phenomenon may be offered by the input-output tables of the major world economies. These tables show increasing input coefficients coming from the industries sectors, fostering the structural change, whereas diminishing inputs coefficients over the time signal which are the regressing industries. An easy way to approach the problem of structural change may be to start from known facts by almost everybody. We are certainly informed on the important innovations that have taken place in some industrial sectors, such as electronic industry and computers. Other sectors have been benefiting from the mentioned innovations. Many of us have certainly noted that the now limited number of clients physically present in banks, as well as the important reduction in the number of employees required for the functioning of banks, together with the possibility for any client of a modern bank to perform the majority of all the elementary banking operations from home or from other places by his own cellular phone or personal computer. For the single banks, several other favorable consequences deserve to be mentioned: lower production costs and higher labor productivity. All this is good and impressive, but the consequences showing up in other sectors like defense industry and modern armaments in general, even if equally impressive, are at the same time source of great concern, at least if men of the present generation do not learn to want peace above all, as human morality requires. Areas of knowledge and information, once considered relatively separated, have become, not always for the good, as I have said, strictly connected. More than 60 years ago, when I decided to become an economist, I was far from thinking that in the future, economists and economic policy makers would need to become also familiar with geopolitics. Yet, I also remember that in the mid-60s, when the University of Bologna, at this university, the Faculty of Political Sciences was originally established, one of the founders, Professor Nino Andreatta, anticipated that over the years to come, the new faculty would become the proper container of most economic and connected disciplines. Before closing, another remark: structural change is not a phenomenon fully described by looking at the involved industrial sectors. Every change in the input-output structure of the industrial system must be accompanied by often very relevant organization changes. This is probably the only strict tie with my talk now with the presents that have been presented before in the day. Before, say, organization changes are costly and cannot be omitted in dynamic models. It may be without meaning that I return for a while to the memory of the birth of the Faculty of Political Science at the University of Bologna. The new faculty had 4 departments, corresponded to 4 specializations in areas: these are the areas: Department of History and Political Sciences, Department of Economic Science, Department of Sociology, Department of Political Administrative Sciences, where the organization problem was carefully considered. It is pleasant to recognize, at a distance of 50 years, that our founding fathers have had good view ahead. Thank you.
Thank you.
So
Thank you,
I don't
Professor
think there
Dada.
are comments to this short talk. In any case, if there are remarks.
I don't know if there are comments, but it has been perfect for driving us to the last consideration about the future research and the general discussion. So I think it was very motivating in this way.
Yes, maybe me and then Howard.
Yeah, great. That's what exactly was suggesting. Thank you very much for closing this.
Thank you.
Thanks again, Professor Dada.
Thank you, and also thank you, Carlo, for your nice recollection of what was to be a very historically, I mean, your references to the political sciences faculties as it was conceived in the very late 60s, because it was a very interesting experiment in interdisciplinarity. I would just add that as a partial correction to what you said, that the 4 branches of the faculty were then called institutes and not departments, because department did not yet exist. And unfortunately, the departmentalization of the university went against the interdisciplinarity spirit, which was behind that faculty of political sciences. That was, anyway, a short remark. But more generally, I think that what this workshop has shown is that there is the need to find spaces for interdisciplinary work. And we had a short conversation over lunchtime also with Professor Lambertini, actually, and who is very well aware of the role of interdisciplinarity in such a topical field like climate science, which is by itself not a science, but a field, actually, an interdisciplinary field. And I think that this workshop, which was hosted by a direct interdisciplinary framework like this academy, basically shows the need for interdisciplinarity, the need for a room, a space in which people from different analytical background can find a common space of interaction. I mean, we had a stunning instance this afternoon, I think, of an interaction between 2 different approaches to the study of essentially of connectivity and interdependence, coming on the one hand from network science, on the other hand from input-output modeling, and clearly from the point of view of mathematical structure, of analytical structure, there is a very, very close connection between those 2 fields. And it's extremely important, as also Professor Quadriocurso was saying a few minutes ago, that we find a way for the different analytical branches basically covering almost the same domain to talk to one another and to learn from each other, actually. Since we are not many people left, of course, due to also a very, very dense set of presentations, but I mean, if also Aura allows me to do that, if there are, since this was, I mean, in the program mentioned also general discussion, so why not? I mean, if there are any people would like to say something in terms of general discussion after this very intense and long afternoon of reflections on the themes of complexity, connectivity, and architecture of socio-economic systems, I would say that questions are welcomed. So if anybody has to say anything, if anybody has to contribute to general discussion, please do it now. If not, I will leave the floor to a person who I think has been the key and fundamental organizer of this workshop, Professor Aura Reggiani.
Thank you, but I would like to say the same to you and Ivano, because of course the friendship also inspiring science. And so I would like to thank all of you. And what I've learned today, I have to say I'm very synthetic because everybody is tired. So according to all the lecture and presentation that I received, I realized, and of course you can agree or disagree, I personally realized that connectivity, that was our focus, has been considered in a dynamic way. So the dynamics of change, the dynamics of connectivity, virtual and physical connectivity, and probably also this COVID time also has been teaching us how connectivity is important, but mostly how connectivity can change, because a link can be disrupted, and as Ariel was teaching, maybe a very important link, a hub. So hub can also, as I said, increase or decrease or dying and so on. And so the links, also our connectivity. And then the network connectivity also of our scientific ideas, our scientific person is important. So also that is important, this dynamics of connectivity among us, as you said before, the interdisciplinary connectivity should be maintained. So then I really hope that this will be the first step for going on with more connectivity among us. And then also for looking also the instrument for not only analyzing the present connectivity, but also to forecast. How can we forecast if a link will be present or dying or improve? So the threshold of strong and weak links is very important to how to establish if a link is very strong or not. What is the measurement? And the policy, of course, as Patrizio Bianchi was saying, the network is vivid. So we have to go on, it's dynamic. And then we have to go on in this, on this line of research, in my view, from many perspectives. And then that's my conclusion. And I would like to thank all of you and Mirko, that has been a marvelous chair.
Thank you, Aura. I forgot, I don't know if a third organizer, which I thanks for everything. Ivano, want to say something or fine? Thank you very much. Thank you, Aura, again. And thank you for the hospitality here at Academic Licei. And
I would like to thank Vincenzo Riccardo Lobuglio, because without him, we couldn't manage. Yes.
Thank you for the technical support, and thank for all of you coming here. And I think we can declare close the today workshop. Thank you again. And I think everything has been recorded. Thank you very much. Thank you.
Have a nice return to your duties. Thank you for coming.